lot of apps who might want verifiable computation to have in-house cryptographers to write these circuits. And as we all know, obviously writing circuits that are not under constraint or just in general secure can be a bit of a challenge. So the more we can make that something that doesn't have to be repeated all the time, that seems kind of nice. You'll see a couple patterns if you look at the list of ZKVMs. One of these is RISC-V, which shows up as the most common underlying ISA for the ZKVM. And the other one is Rust, which shows up as the most common front end for a lot of ZKVMs. And both of these will come up a bit in what I'm going to say when it comes to actually formally verifying ZKVMs and programs that would run on them. So with respect to Ethereum in particular, we actually have quite a few plans to embed ZKVMs within Ethereum, and that includes for the consensus layer. So you can go and see Justin's Beamchain talk at DEF CON. The idea there is that instead of the consensus layer working as it does now, you would instead actually have ZKVMs used to prove the state transition function. And this would be using some combination of multiple ZKVMs. If you look at the slide there, you had RISC-0, Succinct, Jolt, Powder, Nexus, Scroll, and the ZK-Sync ZKVM listed. And if you've seen this list before, that list of potential ZKVMs that we could use has grown quite a bit. We also have native rollups, which are coming up. This is a bit more recent than DEF CON. But the idea with native rollups is to do what feels like to me rollups should have been from the start. But here you would basically be able to expose some kind of execute precompile at the EVM level, and therefore allow rollups to kind of get much closer to the layer 1 execution layer. And again, we would use ZKVMs down the road to actually prove the execution of whatever rollups are doing, instead of having to go through re-execution and the downsides that comes with in terms of scalability. And it's also somewhat reminiscent if you have things like Arbitrum Stylus, and people have been exploring this idea of kind of alternative VMs to be able to execute a wider range of programs. And we've also been thinking about exposing RISC-V as a lower level VM than the EVM, which would give us a bit more flexibility, particularly with respect to rollups that might have state transition functions that are different to the layer 1 EVM state transition function. Performance of these ZKVMs is only getting better. We have a nice new website that's been set up by other people in some foundation called easeproofs.org. You can see some benchmarks here in terms of the time that it takes to prove an EVM block, as well as the cost. All of these benchmarks are on kind of single machine AWS provers. If you do want to scale this down to something that gets close to real-time proving, I think proving all EVM blocks for a year in under 30 seconds per block would be in the range of maybe 150K, 200K, something of that order of magnitude. And then if you wanted real-time proving, which would be less than 12 seconds, or in the context of the beam chain, maybe less than 4 seconds, you would add some number to that. But between kind of hardware improvements, as well as improvements in terms of the proof systems and ZKVM design and engineering, we are getting fairly close to making kind of real-time proving somewhat realistic and affordable for us to use within Ethereum, and presumably a lot of other applications as well. So because we're planning to use ZKVMs quite heavily, they're also going to become security critical. It's obvious that if you have issues in anything ZK, things can blow up fairly quickly. And for that reason, DEF is investing essentially $20 million over the next 2 years, starting a few months ago, to make sure that we can set everything up to formally verify them, but also to develop all the tooling that's required to keep them formally verified down the road, because we expect things to keep changing, both in terms of engineering, but also in terms of the proof systems. And so we're running this big program, which has a lot of grants and a lot of bounties available, and I'll talk a bit about some of the work that's already ongoing and some of the work that's coming up in the future. So we split our kind of task into 3 tracks. The first is the ZKVM track. This one is somewhat self-explanatory. You're looking at the ZKVM. One big thing is obviously the circuit that actually is meant to implement or encode RISC-V semantics into it, or add some other ISA semantics if you're using another ISA. You'd want to make sure that that circuit is actually correct, in some sense, sound and complete. Certainly, if you think of arithmetization, and if you're thinking of it in circuit terms, at least not under constrained and not over constrained. And I'll talk a bit more about this in a second, but essentially you want to make sure that if you are going to get a proof, it's only for a valid computation. You've got the EVM track. This one I think is also fairly straightforward. We have many implementations of the EVM, maybe only one in Rust so far that runs on ZKVMs, but we expect that to expand in the future. And the key thing is to make sure that if we are going to have formally verified ZKVMs on which an EVM is running, that we also have EVMs that are bug-free. And for that, we'll be basically checking that if you take an EVM and you compile it to a ZKVM, most likely a RISC-V ZKVM, then that compiled EVM actually matches the behavior of a formal EVM specification, and we're fairly lucky to have a couple EVM specifications that we can already use. And then the last track is about cryptography. The ZK part, or succinct, if not ZK, of ZKVMs, is that you have a proof system that has to run on top of them. Proof systems have been changing quite a bit. There's been obviously a lot of people working on new proof systems all the time, and we want to make sure that if you're building a ZKVM, you can switch to a new proof system without too much worry about security. And for us, this means developing executable specifications of proof systems that are formally verified, in the sense that they're directly tied to a security proof for the expected security parameter, and then making sure that we can verify actual implementations in Rust of these proof systems against our executable specifications. So to get into a bit more detail about this, with the ZKVM track, we're working off of the reference cell RISC-V specification. We recently had a grant that's made a lot of progress towards adding a backend to Sail, which is a language for defining ISAs. And this means we can extract the reference RISC-V specifications to Lean, and we already have extractions that existed before to Rock, Hawthorne, and Isabel. So the specification for RISC-V ends up being quite big. I think the Lean spec at the moment is about 100,000 lines of code. We'll do a bit of massaging to try to put that into a proof for a circuit that's meant to encode this. But we are aiming to kind of go from something that feels like the best ground truth possible, and that would be the reference RISC-V specification. And then when it comes to actually looking at the circuit, we've got a couple of approaches, and I think here we're trying a few approaches from the start, and we'll streamline things as we go along. So for things like Jolt or Plonky3, which are already used by ZKVMs that are fairly well developed, Plonky3 in particular is, I think by far the most widely used implementation of a proof system that ZKVMs rely on. We'll be just developing extractions for these two proof assistants, whether that's Rock or Lean. And you'll hear a bit about the extraction from Jolt to Lean in a bit later today from James. But these are very nice. We can get the circuits into proof system. We can verify properties of these circuits. But down the road, because people are writing circuits in many, many different DSLs, and people are probably going to keep coming up with many, many other DSLs, we are also going to try other less kind of naive ways of doing things. One of these is to just write circuits directly in Lean. We have a bit of experimentation going on with this, with ZK security in particular. I see some thumbs up, which is always good. This is actually quite interesting. You can, Lean in particular is just quite a nice functional programming language, so it's not that bad to just try to write, kind of reasonable code in it. And the nice thing is then you can just prove your circuit as you write it, and you can get it to a point where you have these nice generic composition theorems, where if you have completeness and soundness that's been shown for a subcircuit, you can get a proof of completeness and soundness for an entire circuit composed of sound and complete subcircuits. We started this fairly recently with, as I said, ZK Security, who have some in-house expertise on both looking at a lot of circuits as part of their security work, but also some in-house expertise of actually coming up with circuit DSLs. And Greg in particular, I think wrote a TypeScript-based circuit DSL when he was working at O1 Labs. The nice thing here, it also means that because you're proving things as you go along and you have a proof that's directly tied to your circuit, when you want to add an optimization to your circuit manually, you can verify that it doesn't break your proof or repair the proof accordingly. And so you can also optimize further, or with a lot more confidence than if you're just trying to do manual optimizations on some Rust code or some Circom code or some other kind of DSL code, where you're really just kind of hoping for the best and trying to reason maybe on pen and paper, or maybe not even on pen and paper, about the correctness of what you're doing. The interesting thing here is to figure out, can we write circuits in a proof assistant and have these circuits actually be performant? One way to do this is maybe to just kind of, extract a description of the circuit to Rust in a faster language, and we'll be playing a bit around with this in the future. And we'll also try to work from what we have now, which at the moment is a kind of prototype proof of concept of a Keccak precompile, which is has a fairly surprisingly nice proof attached to it, but we'll try to obviously build this up to some kind of VM or subset of RISC-V circuit in a few months. Now, the other approach that we can try, which is to mainly deal with the fact that people are using many DSLs and can come up with many more other DSLs, is to actually just develop a nice IR for circuits. This has been tried before. There's always a risk of just adding another IR to the stack that people are not necessarily going to choose. But we are actually doing this. So with Veridies in particular, they've been developing an MLIR dialect for circuits that should provide a nice unified layer to work from in terms of verification, as well as not just verification, but verified and automatic optimization passes and things of that kind. That MLR dialect will be open source in about a month, and then we'll be building up tooling around it. The initial integration with a high-level language will be with Zergin, because Zergin has its own links to MLIR, which makes it easy, but we'll be expanding the integration to that as much as we can, and hopefully it means that if someone then later on decides to do a new circuit DSL, from the start they can think about compiling down to that MLR dialect and benefiting from all the tooling that will be going on around this, which should be, hopefully should work well, and hopefully it enables people to write circuits in an easier way because they don't need to optimize them by hand as much, benefiting from whatever optimization passes we develop at that IR level. But also it allows us to embed with a lot of efforts that are going on with verifying MLR dialect semantics in proof assistance like Lean, which is also doable in ROC. And we'll be developing extractions from that dialect to Lean and ROC with the aim that we can apply a lot of SMT solver-based tooling at the MLR dialect level directly, but if we can also extract them to proof assistance, any proof obligations that we can't do with SMTs, we can then verify manually in a proof assistant. The other thing that's very much on our mind, and it is somewhat, maybe not trivial, but feels like it should be doable, is to just try and develop kind of general purpose proof infrastructure for circuits. And this means figuring out how to represent circuits in a nice way, figuring out good tactics in proof of systems to prove things about circuits, particularly when it comes to things like modular arithmetic and other kind of manipulations of integers, or finite field elements rather. And in particular, something that's come up with circuits a lot, which has been actually quite helpful in terms of verifying circuits, is the use of lookups. The nice thing here, especially if you look at the dual circuits, you don't have a lot of gates, you just have lookups for every instruction. You can think about just formally verifying the lookups themselves, and then you can kind of probably compose proofs for circuits from the proofs that you have for the lookups themselves, and that seems quite attractive because you manage to get something that, one, obviously you get much simpler circuits. The difference in circuits for different arithmetizations when you're only using lookups become much lesser. You can kind of squint at an air circuit that just does lookups and an R1CS circuit that just does lookups, and they don't look as different as they do for maybe some of the older kind of circuits that were just a ton of gates. And if you could then compose proofs from formalizations of the lookup arguments, maybe things become a lot more easy to deal with. Now, for the EVM track, so we're very lucky to have existing formal specs for the EVM. We've got some in K, developed by Runtime Verification, which was the first ones to actually develop formal specification of the EVM, or formal semantics. We've got one in Lean, developed by Nethermind, which I think as of recently is the one that passes the most conformance tests, so shout out to them. And then we've got one in ACL2 developed by Kestrel, and one in Hall 4 developed by Veriferium, which are both somewhat work in progress, but it wouldn't be too much effort to bring them up to date as soon as we need to use them. The goal of using these specifications is to be able to verify implementations of the EVM against these, and we're already doing this now with REVM. So REVM is the kind of canonical Rust implementation of the EVM, at least until maybe Lambda class finish of their work on LEVM. And so this means that because RISC-V ZKVMs primarily use Rust as a front end, this is the EVM implementation that every ZKVM uses at the moment. So we're already verifying this against KVM. This is done in collaboration with Runtime Verification. And we're also then developing a Lean backend for K, which will allow us to make sure that the Lean specification of the EVM and the K specification of the EVM are actually equivalent, as a nice sanity check that we haven't messed up the specs. Or at least if we've messed them up in the same way independently, and that would be interesting to find out as well. We're also in collaboration with Baz, and Carl Palmskog, who is at KTH, Baz is at our house, developing a canonical ROC implementation of the EVM. And the idea there is not just to have a formal spec, But to have an actual fully fledged implementation that can be used, can be performant, and can be compiled via a certified computation pipeline, which will then save us the trouble of having to verify an actual implementation against it. This would also include precompiles, using the fact that Rock obviously is well equipped to do all of that, and we'll have more updates about this in a couple months. The big question here for us, I think, is maybe not so much how to verify EVM implementations. To some extent, it's somewhat, standard program verification up to the amount of work that it requires. What we're really thinking about is how do we deal with the fact that obviously we have many more EVM implementations that need to be verified, even if we're thinking about things like client diversity. That might become less important as implementations of EVM get formally verified, but they still remain important just to maintain maybe some diversity in the software stack, and to prevent anything kind of blowing up, because there are always some small caveats to formal verification, as well as just allowing people to use something they don't want to use, but to explore different ways of implementing the EVM, which is something that helps push performance in the long run. So verifying other implementations of EVM partially depends on just ZKVMs adopting other implementations of the EVM, and thinking especially with respect to applying ZKVMs to the Beam chain. There we have obviously kind of clients in Go, C#, Java, Zig, whatever people will develop. And so at some point, we'll get around to verifying more implementations, and that'll be obviously using the fact that we have multiple other specifications and therefore teams that can do this kind of work in parallel without becoming a big bottleneck. Now, with respect to cryptography, I'll actually talk a bit more in detail about this in about 10 minutes or so. We're combining two talks where I'll talk a bit about ZKlib. But the main thing that we're developing at the moment is ZKlib. This is a lean library of executable implementations of proof systems, or executable specifications of proof systems, rather, that will be directly tied to proofs in lean for those proof systems. This is fairly early days. We recently had a complete proof pass for a one-round sum check protocol. Most of that involved actually just fixing things in terms of the infrastructure. And from this, we've learned a few more things to fix, but we'll be expanding this up to handling more proof systems. And we'll be doing Spartan, Friester, over the next couple months, and kind of growing that endlessly. And we're very much looking forward to having the library in a state where we're not making breaking changes anymore, and where people can start contributing kind of whatever proof system they would like down the road. This doesn't have to be proof systems that are specific to the Ethereum ecosystem. Any kind of IOP should be implementable within this library. And yeah, there'll be a few more details about this in about 10 minutes time. But the next thing, once we have proof systems that are actually implemented in ZKlib, will be to actually verify implementations of these proof systems, most likely written in Rust against ZKlib. And here we'll be looking at tooling like Hax or Anus that have been developed independently for kind of Rust verification and linking Rust to proof assistance. Now, there are a couple challenges to everything that we're doing. Unsurprisingly, I think everyone has a sense that formal verification is fairly well known as being hard. One big challenge on top of formal verification being hard is that ZKVMs are incredibly complex. They're fairly new technology, which means that also they're changing fairly rapidly. There are a lot of design decisions that you can make in terms of how modular you are or how unmodular you are. RISC-V, as a spec, is fairly modular. So there's accommodating the fact that people might use different RISC-V extensions, even if for the moment maybe the only split is between kind of using a 32-bit or 64-bit RISC-V implementation. And there's a lot of ZKVMs, right? So when we're talking about, there's a lot of different trade-offs and design decisions you make for ZKVMs. Right now, as you sort of start, we've got about 20 ZKVMs. Maybe 10 to 15 of these are kind of RISC-V ZKVMs. That's a lot of software diversity, even if a lot of it is written in Rust, because people are writing it in different ways that may be more or less amenable to form verification. Because these ZKVMs are also changing all the time, and by change I mean that they might be going through complete rewrites on a yearly basis to some extent, maintenance of any kind of form verification status is very hard, and the same applies to the EVM. So the EVM has new opcodes that come fairly regularly, other kind of changes. We've got gas pricing changes that might come, EOF that a lot of people have been complaining about on Twitter for some reason is coming as well. And so trying to make sure that when we do verify something and spend a lot of time and effort on verifying these things, that we can maybe automate that maintenance process, ideally just like put it into CI. It's something that we're trying to experiment with and trying to work on, and obviously a big goal for us, because otherwise we'll be verifying a lot of things that will soon be out of date, and that doesn't really help anyone. And to do that, what we really need is kind of better tooling and libraries to make this much more practical. One goal for us is that we're putting a lot of money into this upfront, and the idea is essentially that by putting a lot of money up front, we can identify the tooling that needs to be developed, we can develop it, we can set up a way to maintain that tooling, we can then show how to use that tooling to verify things, and hopefully at the end of this kind of 2-year project, we have not only verified some key artifacts, but also we've set things up so that the ZKVM teams themselves understand exactly how to keep things going, but also that when they talk to a form verification team as contractors, they have a kind of set of standard tooling that they can use to make things a lot easier and faster than it is now. Now, in terms of measuring progress, so Justin Saylor wrote a blog recently where he kind of came up with these kind of stages of, stage 1A is formally verifying the soundness for the underlying PIP in the proof system, formally verifying, the polynomial commitment scheme, kind of dealing with Fiat Shamir, you've heard a lot about Fiat Shamir if you were here on day one. And then obviously kind of bundling everything together, and then obviously also verifying the implementations for the prover and the verifier, which is kind of, we're very much on board with this, and I think it's a fantastic thing that at least people who are developing ZKVMs, like the Jort one in Justin Saylor's case, that everyone is thinking actively about this, and everyone has been mostly on board about how to progress and how to try and get form verification embedded into ZKVMs, but also hopefully embedded into the kind of continuous development process that they go into. One thing that's quite important, obviously, for any big project is trying to find some notion of success that we want to attain and that we can evaluate ourselves against. So I think the goal for me is that the ZKVMs, as a result of our effort, should be better. And that obviously means more secure, which is important and is always a key goal of form verification. But also, actually, we'd like them to be kind of more performant and more usable than they are now. Obviously, in terms of performance, I think the overhead of running something in ZKVM and proving it against just running it, on your own hardware and obviously not proving anything, it's probably 100,000x, 1,000,000x. This is obviously not great. It'd be great to get improvements both from engineering and from kind of new proof systems and things like this. And obviously, everyone is working hard on this. And I'd like form verification to some extent not be something that feels like a slowdown and something that requires code freezes, but rather something that actually allows people to push a bit further, a bit faster, with a bit more confidence. And one reason for believing that this is actually kind of feasible and not just a bit of a pipe dream is that we've seen kind of form verification also be adopted kind of increasingly in industry, and AWS in particular has been doing quite a good job about this. And they've got a few blog posts now that are around that are exactly around the fact that by verifying optimizations that they couldn't possibly kind of audit, or even fuzzing might not be appropriate, they've been able to get big performance increases on kind of key parts of their stack, especially when it comes to cryptography, and therefore push performance as a result of using form verification. And by kind of better embedding form verification in their development process, they've realized that in the end, actually, they write kind of better, more efficient code. Because one nice thing about form verification is that it's one thing that helps you reason about your code to quite a high level. And a lot of times we see it now. People do find optimizations as they formally verify things. I think going back to Jolt, they had a paper that will be at FC this year, where they were formalizing some parts of the Jolt circuits, and they were reducing the size of some lookup tables by, I think, 87%. So you can actually get kind of good performance improvements, hopefully, from form verification. And I think if people want to do kind of crazy low-level sketchy optimizations, the best way to accommodate this is to try and set up tooling so that we can verify what they're doing along the way and help them just push things further without the risk of them feeling like they're breaking something and not optimizing as hard as they could, or actually breaking something, which would also be obviously a bit of a disaster. So we have, there's a website set up, there's an email set up, there's a GitHub organization set up where a few of the projects are already hosted and a few more will appear soon. I've seen that what we're doing is obviously open source and gets open source, at some point, if not immediately. And if you'd like to get involved, obviously, like I said, we have grants, bounties. You can talk to me about it. You can go and see the website, or you can send an email to the email address that's on the screen now. I'm going to go straight into the second half of this talk, which is about ZK specifically, like I promised. I'll caveat this just by saying that ZKlib was meant to be presented by Quang Dao, who's a PhD student at CMU, who's been doing fantastic work on this. He unfortunately couldn't make it because of last-minute visa issues, which is unfortunately something that happens far too much. So I'll be subbing in and doing my best to give justice to the slides that he prepared. And also say that, luckily for us, right before he found out that he couldn't come, we did have a recorded version of this talk as part of a public update call that we did for the ZKVM form verification project that we're doing. And so you can find his version of the talk online on YouTube already. There's no link on the slides, but if you ask me, I can send you the link, or if you just Google, kind of ZKVM, verified ZKVM on YouTube, the channel should come up and you should be able to find it there. So like I said earlier, ZKlib is this library of proof systems in Lean. That's kind of fairly early days, but I'll talk essentially a bit about how we're trying to approach things and how we're trying to think about formalizing these proof systems, especially with respect to modularity for the proofs. So I don't need to reintroduce the project, I've just talked about it for 30 minutes. But just for context, you have somewhat of a kind of range of tasks from the back end to the implementation to the front end, and ZKlib is very much about the IAPs, which I'll be talking about now. So the goal for ZKlib is just to mechanize or formalize the security proofs of current IAP-based NOCs, and to be able to have executable implementations of these verified SNOC implementations. Specifications. And I'll say obviously verified here means the high-level source code. We haven't started messing around with verified implementations in the sense that they go through a verified or certified compilation pipeline. Maybe that's something that we can try and do later on. So the main thing for us is that we'd like to be able to specify in proofs NOC secure, but we'd like to do this in a way that makes sense, because it's already quite hard to specify them and to prove them secure and proof resistant. So the key thing for us is to be able to have proofs that are very modular, and therefore you can compose in as nice a way as possible, so that when we do other proof systems that maybe have similar patterns in them, maybe they, a lot of proof systems end up using some check in some way or form, and you have a few patterns that come up like this, we can reuse a lot of the, past proofs that we've used and a lot of tactics, and just have a nice kind of proof structure that is repeated. And so to do this, the idea is to develop some kind of core language and to think about program logics that could be used for interactive RCore reductions in particular. We'd like to kind of clarify some existing constructions and just kind of streamline security proofs in general. Because if you look at the literature, it's fairly clear that actually, the pen and paper literature has been going towards more modular proofs anyway. And it's kind of the past few years, obviously, you've had the split between the polynomial commitment scheme and the IOP has been kind of much clearer than it was maybe a few more years ago. And people are just getting more modular in practice, so we're not doing, I think, anything too radical. We're just trying to push this further, and we think that maybe formalizing things is a good way to kind of tidy things up where we can. Every now and then you look back and you look at some old protocols that didn't mention some check, and you realize that actually maybe it was just a some check. Or you look at something like Fry. You can look at the original paper. You can look at the Basefield paper, and there's a kind of reframing as Fry in terms of a more linear algebraic framework. And so we're looking at these things and trying to figure out what is maybe a smart way to formalize these in a way that is kind of easier to reuse and to apply to different proof systems, and also to make our lives easier, because if we want to cover a lot of proof systems, that means being able to scale up our verification effort and not just grinding out kind of hard proofs all the time, when we could be a bit smarter and save ourselves some trouble. So I'll quickly talk a bit about what an IAP-based NOC looks like in that context. This is ZKProof, so a lot of people will probably be familiar. You can start with an interactive Oracle proof. You've got messages through an Oracle. You have a commitment scheme, you get an interactive proof, you then apply Fiat Chamé, and then you get a SNOC, which allows you to prove that some witness that satisfies some relation or something like this, which can be verified with a public input. So the way that you can construct IAPs, or one way of doing this is to just do it via a series of interactive RCore reductions. So you can take your intended IAP, and you can kind of reframe this in terms of a series of interactive RCore reductions, which are just intermediate steps between what you start with and what you actually want to end up with. So we're already seeing a bit of kind of modularity come up in some sense here, and I'm going to push this a bit further. So let's take the subject protocol as an example, and let's take a very simplified version of a subject protocol as an example, where you just got a bivariate polynomial. And you've got this relation maybe let's call it an input relation here, which is obviously what you start with, which is just sum of the polynomial over all the values of the variables equals to t. And at the end of the subject protocol, you're going to get some relation which is based on challenges R1 and R2 equals to something else. So we've got kind of 2 rounds here of the prover sending something to the verifier sending back a challenge, and then at the end you get the intended result. If you're not familiar with subject protocol, I'll say nothing that I'm going to say kind of depends too much on exactly how the subject protocol works itself. It's just trying to illustrate how we're trying to break things down in as modular a way as possible. And in particular, I want to try to get a bit of a link to kind of program logics, to try to reframe IORs in terms of program logics and to see how we can get nice composition rules based off of that. So back to our subject protocol diagram here. If we just zoom in on the first round of the prover sending S1 and the verifier sending back a random challenge R1, you start with your polynomial. You obviously kind of fix one of the variables, so you get this polynomial S1 here. And then compared to what I had earlier, what I've done here is just introduce this kind of middle relation. So that would be kind of some intermediate reduction of knowledge. You'll see here that this is still just a bunch of polynomials, but from that you can kind of go even further. And if you zoom in on the part that's highlighted here in the kind of yellow box, you can split this up even more, and you can have some kind of R mid prime relation here. And the nice thing here is that by kind of breaking things down as much as possible, you've ended up with S1 here, which is just P of x and then 0 and P in x and 1. And for the verifier to check this is deterministic. So there's kind of the probability of that failing is 0, which is all great. And then you end up with your kind of mid-prime intermediate relation here. And the property of that is just going to be d over the size of the field. This is just a Schwarzschild lemma, which comes up if you try to prove the soundness of the subject protocol as usual. But the nice thing here is that by kind of isolating things that have property 0 failing and just recovering the one thing that actually has some non-zero property of failing with the kind of normal bound that comes from Schwarzschild lemma, you can get round by round guarantees essentially for free. And this is quite attractive, right? Because you can think of, if you start instantiating other protocols in a similar manner, you can probably do the same thing again, and you can start to reuse tactics, and you can start to sub in different components of proofs for parts of protocols that kind of look like each other. And at the end, this is the kind of R-mid relationship here, which was right here as well. So you're not kind of changing the protocol or anything, you're just breaking this thing down as much as possible. You can push it even a bit further if you want, and just kind of simplify things a bit further if you want. And you can define this kind of virtual polynomial here, P1x, which is just kind of what it was on the past slide, but slightly written in terms of one polynomial. And we can call these virtual polynomials. You can kind of call them something else if you like. But essentially, we're just trying to simplify things as much as possible, so that when we look at a single message going over as part of the protocol, we can then just have small proofs about this and compose things from this. And what we're trying to get to here is some connection to kind of Hoare-style program verification. So in Hoare-style program verification, you've got this notion of Hoare triples, where you've got given a program C, you might have you execute it with some precondition P, and you get to some postcondition Q. And this is what a lot of program verification is based on. You get these nice kind of rules to kind of deal with these logics, and we'd like to get something maybe similar in terms of reductions. So you would have some reduction PV for the prover verifier, and when you execute that reduction on something satisfying R1, you would then get something that satisfies R2 and be able to reason about this with some appropriate logic that would apply to interactive vocal reductions. So this is somewhat, I think, our goal here, or certainly the goal that Kwong has been pushing, which I think seems very promising. And like I said, we have now kind of very basic one-round sum check proofs that's kind of passed completely, and we'll be expanding that to kind of more complicated examples. But hopefully, doing things in a normal way will mean that the more complicated examples don't become that much more complicated. So I'll talk a bit, just to finish up on the current state of ZKlib. So currently, as I said, we've got some definitions of interactive awkward reductions. We've also been working on a kind of competition-friendly polynomial data type in Lean. This would be something that basically just kind of can actually run in some reasonable amount of time, and then developing an isomorphism between that polynomial data type and the polynomial type that's used in MassLib to do all the proofs that we rely on. And like I said, we've got kind of a specification and a proofs of security for a single round of sum check, and we'll be kind of expanding on that to obviously multiple rounds of sum check with round-by-round knowledge soundness, and then into bigger IOPs. So we're very interested in kind of pushing competitive IORs and having nice proofs that they preserve security. So this just goes back to what I was saying about modularity and thinking about composition. And like I said, I think in the first part of my talk, we're working towards having executable specs that are directly tied to security proofs, and so we'll be doing this for the Spartan IOP, and then we've also got blueprints starting very soon for Fry, Stir, and Were. So Fry will be with the help of Nethermind, and Stir and Were will be with the help of Least Authority. Once we have these blueprints set up, one thing that we're also intending to do is to set bounties for specific theorems. One nice thing about Lean, or doing things in a proof instance in general, is that obviously it checks proofs for you. And so blueprints, for context, are just a dependency graph of theorem statements that need to be proven to get to a final result. Anyone should be able to look at the blueprint, look at a theorem statement that needs to be proven. Some of these might be quite simple. In particular, some of these might just be things about Reed-Solomon codes that shouldn't be too complicated. And anyone can then jump in, do a pull request, submit a valid proof, get a bounty that's been fixed ahead of time for completing that proof. And this should hopefully allow us to kind of parallelize proving efforts, get more people involved, have a lot of tasks from very easy to very hard. And if anyone wants to prove the proximity gaps conjecture in Lean and save me the trouble of having to figure out that their proof is correct, we will be stating it in Lean, and you can just submit a proof request, and we'll see what the Lean type checker has to say about it. And similarly for other conjectures, right? We've got some longer-term goals, obviously, past these kind of short-term plan work. This is just kind of formalizing the compilation steps once we want to get to a complete proof system. Kind of basic notions like rewinding of knowledge soundness and zero knowledge that are kind of traditionally quite hard to formalize anyway. We'll see what progress we make on that, but obviously we'll get there in the end. And also obviously trying to improve performance. So this is either matching our executable specifications to Rust implementations that are actually faster than people use in production, but also potentially seeing how far we can push code generation from Lean. And ideally, it would be nice to get executable specs that execute at least fast enough for differential fuzzing, if not to be run in production. We'll be producing some tutorials and basically onboarding material for ZKlib. To try and get as many people involved as possible. It's a open source library like any other, and if anyone has followed what's happening in Lean with things like MassLib, it does seem like there's a lot of potential to build up kind of these nice comprehensive libraries without also kind of breaking them down into a horrible mess. And it would be fantastic if this could be a nice contribution, not just in terms of form verification, but because we're thinking a lot about kind of streamlining proofs and clarifying some proofs. And Kwong in particular is a kind of genuine cryptographer before being a Lean or form verification person. And we're hopefully kind of aiming to have some contribution back that flows back into cryptography and have a bit of a feedback loop between both. And to not just be formalizing things for the sake of it. And in particular, the audience for this library, we're not thinking of just form verification people. We're trying to make this as usable as possible for day-to-day cryptographers. Some cryptographers obviously already write reference implementations, some don't, but we're working quite hard to make sure that things that you just kind of use out of the box, like Fiat Jamais, like other cryptographic gadgets, are usable in the same way in Lean, usable in a simple way, so that what you're left with is proving the information theoretic part of your IP as part of the proof system, and the truly kind of new parts of whatever new proof system you've come up with, rather than wrestling with trying to put in some kind of bastardized, formalized version of Fiat Jamais in there. And it would be fantastic, obviously, if anyone wants to try it, give us feedback about what would make it more usable, and kind of, maybe think and experiment with trying to, kind of use this library, kind of, to formalize their proofs, or to just have a look at what it would mean for them to formalize their proofs and what kind of challenge that would entail. Obviously, on the mathematics side with MathLab, there's a lot of kind of big, now mainstream mathematics projects going on, which has been very exciting. Some people have managed to formalize entire papers before peer review finishes. Peer review for them sometimes takes a bit longer than it does for us because they kind of journals more than conferences. But it would be very nice if we can kind of, get things to a point where adding a new proof system that comes out in a paper or a preprint on ePrint doesn't take too long and becomes a very tractable task that can produce kind of nice reference implementations for people to then base, kind of actual implementations that will run in production off of, and maybe kind of differentially fuzz and formally verify against down the line. So just as a quick summary, and just reiterating a few things, I think everyone here will probably agree that formally verifying snarks is important. We all know the risks of things blowing up, and we're trying to kind of help in that direction with ZKLib in particular for IOP-based snarks, following the kind of key ideas of reductions as the main building block, and trying to make a connection with program logics and program verification ideas that will hopefully will help us kind of get nice composition theorems and to kind of make this a lot easier and manageable. That's it from me. Obviously, thanks for bearing with a double talk and the rambling that goes with it. I think we might have a bit of time for questions. And so, yeah, any questions, I'm happy to answer.
First of all, thank you so much, Alex Hicks, for this talk. It was a double talk, but it was like fascinating and went over all the explanations very clearly. Raise your hand if you have a question. All the people with, no, just so I know how many questions. All right, go ahead.
Okay, so I'm going to be one of these people at a conference who, instead of a question, I'm going to make some observations. Sorry. So it's a great, those were great talks, and thanks to the other presenter who couldn't be here. So what I got out of it was that there are some simplification strategies that we can use. I've written down 4 of them. The first is to focus on sort of fewer alternatives that people have already congregated around. So Rust, RISC-V, Lean, MLIR, and so on, but not proof systems, because the most obvious thing is that you have to standardize on proof systems, but they're changing too fast. Yeah. And actually, there are enough commonalities between proof systems and what they're doing that we don't need to fix those, and various projects will have different trade-offs that require use of different proof systems. The second is, if we write directly in proof-assistant languages, like Lean, with macro systems that support embedded DSLs, then that means that we're not having to freeze code in order to verify it. That is directly the language that we're writing it. If it's expressive enough, then we don't necessarily need to write in a conventional programming language like Rust, because we can extract to that, or we can have the DSL compiled directly to something efficient. Then the third thing is, so lookups, people sometimes think of lookups as functions. I would encourage everyone to think of them as relations, because that supports non-determinism. And you can also think of a polynomial gate as a relation. So basically, all you have is a bag of variables and sort of relational constraints between the variables. And essentially, everything in a circuit can be expressed like that, except that. So sometimes you use the technique where so you constrain part of a circuit, and then with those variables committed to, you extract another challenge using Fiat-Shamir, and then the rest of the circuit can be dependent on that challenge. And that's very often gives a protocol is the same thing. So we have this isomorphism between circuits and protocols. It seems to me that if we can put those in the same model and use because this sequentiality, so the adversary does not know the challenge until a certain point, is why you need sequential logics rather than just a purely relational logic. So yeah, if we can view circuits and protocols as essentially the same kind of thing, that potentially makes it easier to do end-to-end verification of a system of circuits and protocols. Okay.
Thanks, Dara. Now a real question.
Yeah, so I got the impression from the presentation here that a lot of the verification efforts are very, very focused on completeness and soundness, and I saw only passing mention to zero knowledge.
Most ZK VMs on zero knowledge at the moment. The ZK is a lie.
This is fair. I guess I'm wondering where you see it fitting into the long-term roadmap here of, down the road having actual ZK, in an ecosystem like Ethereum that is verifiable through a framework like this.
Yeah, so I think, so kind of like I said here, we are interested in like mechanizing these notions, zero knowledge as well. We'll get to that. I think obviously we'll try to get to that at least maybe before, ZK VMs truly become ZK. And I think what will enable that is just kind of better performance, because at the moment you can't really do client-side proving, and so if you're sending your witness over to a server anyway, it's not much point in calling it ZK. But yeah, it would be nice to get to that. It would be very exciting to have kind of actual ZK on Ethereum. It'll be a bit of time, and some of it will not just depend on me, so I don't want to commit other people to timelines. But we'll get there. But not with ZK VMs. Oh. Then problem solved.
Thanks for a nice talk. You mentioned security proofs, so are you doing them in the symbolic model or the computational model, or is it something different?
It's one of these things that we end up talking about, and then no kind of final opinion on it. At the moment, it's maybe a bit more computational, but I don't want to kind of commit Kong and the others to something right now.
But it's no general game hopping technique, or?
Not at the moment. I think maybe once we have a few more things fully fleshed out, we'll think about how to refine that. But nothing set in stone at the moment.
Thanks.
Hi. You spoke about using Lean to actually sort of like compile from Lean directly to something else, right? So I guess you're using Lean as a functional language in that respect, regardless of its proofing abilities. Did you consider Haskell? Are you considering Haskell?
I can't say that we did. I would say that none of us are Haskellists. That would be the one big reason. But also the ability to kind of co-locate your proofs directly with your code is quite attractive. Presumably, I suppose that if we did everything in Haskell, maybe we'd proof things in Actor or something else. But yeah, no Haskell involvement so far. Sorry.
So translating from dependent types to Haskell has been available in Rock for ages, and you can do the same thing for Lean.
More questions?
Okay. You mentioned you'd only done one step of sum check, but then why wouldn't it work for, the entire, what does it mean by one step, and why wouldn't it work?
It should probably work for more rounds.
Okay.
It's just that we had a lot of fixing to do with respect to the underlying Oracle library and getting a bunch of sim lemmas to basically deal with the entire kind of messaging part, to just leave out the information theoretic part of the proof to fill in manually. That took a lot of work. Now that's fixed, we can start adding more rounds and reuse that. Yeah, it shouldn't be kind of too challenging.
The whole goal of what your slide said was to do these mini reductions in the second one is exactly the same as the first one, right?
Yeah, so that's why it should follow. But when I say like we just did some check, I mean like the commit was like a week ago.
Oh, okay, I see. Okay, all right, thanks.
I have a question related to like the first part of the talk, when you were talking about the requirement that you want to check from the polynomial commitment scheme, and you were saying any kind of security from standard cryptographic assumption to idealized model. Like, how from the point of view of industry is seen, because there is, at least from the theoretician point of view, we know that there is a big difference between having a proof from a simple assumption and on the other side having a proof from idealized model and anything in between, particularly because the more you move towards idealized model, the harder it is to formalize it or to verify it. How this is seen from the point of view of industry?
Like how hard is it to formalize?
How hard it is to formalize, how different it is in the term of how different it is in terms of how do you believe in the proof? Would you also implement the scheme regardless? Like, what is the point from us to try to make good proof if industry see all the proof at the same level, or does it actually see all the proof at the same level? I know it's a very general question, but I don't get any answer when I try to make this question, so I try every time. Maybe someday I will get an answer, I don't know.
So I mean, I'd say that we try to prove things at the same level as they appear on paper. We're obviously not trying to add any kind of assumptions or to tweak any kind of security model. That would be my short answer. My long answer would be when we try to prove something big, we'll see what happens there. But you know, the plan is to not kind of compromise, and for any compromise, obviously, to at least kind of document it, you know, very explicitly. We'll see. Ask me in 6 months, and we'll have something bigger to discuss and see how we've done.
Okay, thank you very much, Alex.
Thank you.
Okay, hello. I just wanted to give a quick update on the standardization effort for Sigma protocols and Fia Shamir, especially because I'm starting to push it a little bit more at the IATF level, and I think I want to keep in touch so that also this community is aware of the progress that we're doing there. My name is Michele Roux. I've been speaking about this by now for a couple of years, and you can see more details of my strategy and how I'm going about it in the previous year's talk. But roughly speaking, maybe differently from some other approaches of specification here, I've been taking more of a bottom-up approach where I'm trying to specify Fia Shamir and Sigma protocols and trying to take care of that. And I have 2 IATF specifications that I will be trying to push in the next years. And with the idea that from there we can create a nice infrastructure that will allow to build interactive Oracle proof and in the end more advanced protocols. Just very quickly, Fia Shamir transformation, pretty sure you're aware of it. It's what it allows an interactive proof to become non-interactive. And our approach here has been to rely on well-established foundations that in symmetric cryptography and try to have a provable security approach. As you may have noticed already by the talk on the first day, despite the Fia Shamir heuristic is very old, we're still far from understanding all the details of it. And trying to go in this direction, I just published, also thanks to the big help of Alessandro, a paper that tries to prove the Fia Shamir transformation all the way down to the permutation function that is used in duplex sponges. And my hope here is that it will also help in the formal verification of of the Fisher-Shamir transformation and sort of establish what are the lemmas and the theorem that need to be proven along the way. Once we have a Fisher-Shamir transformation, what is the simplest interactive protocol that we can transform into non-interactive? These are Sigma protocols. The objective here, at least the minimum viable product here for me, is to do Maurer proofs, which are proofs of knowledge that prove the preimage X of a public function phi. And they are so simple that I can literally write them on a slide. And here I want to say where these proofs are already used. And in fact, I am grouping them by RSC that are already published. And there is 2 of them that already use this type of proofs, Maurer proofs. And there is a call for multi-party threshold cryptography by NIST that is most likely to use them. There is a certain number of IETF drafts that will have to rely on these sort of proofs. And even new proposals like the one from Google or the Decentralized Identity Initiative that might have to rely on more intense infrastructure on SNARKs, they will still have to rely on Fisher-Shamir. And so the hope there is that we can all converge into using the same components. And I do, besides the stuff that is happening in standards, there are also deployments. They are now deployed already in Signal and Tor, but also they are deployed in big tech industries. And I do think that a lot of public good sort of non-profit open source organizations do need this work to happen because they don't have the capacity to hire cryptographers that are expert in zero knowledge or to push for the standardization effort themselves. And my hope, I think that if we don't manage to get all these specifications to converge on the same spec, on the one hand, we will have a lot of duplicated code and different ways of doing the same operations. And on the other, we might expose ourselves to reuse attacks. And it's going to be much harder to understand the security of this protocol when when copy-pasted across different environments. I'm leaving here the link to the sort of homepage for the true specifications. And yeah, I'm here if you have a quick question.
So any quick questions now? But also you're around, right? If we want to have
of course.
Longer, and we're going to have a conversation about standardization and the role of this organization, ZKProof.org, for helping and promoting this later in the day. So it's a whole workshop dedicated for that.
So I think this is very exciting. We also discussed it, I think, last year or the year before at HEX. So this should really help formalization. So zero knowledge or Sigma proofs have been formalized at least 3 times in EasyCrypt, in CryptHall, and in SSProof. It would be really good to learn from those, I think.
Yeah.
And also the reverse.
Is there a formalization effort that's linked to what you showed?
Beside what Bassem mentioned, I don't know. I think the difference that let me roll back. No, there is not. I think some components have been proven, bits and pieces, but there is no full component that there is no infrastructure that has been built to prove the full spec. I've been trying to get the formal method people interested. I think it's getting there, but at least when I started, I think 3 years ago, it was still perceived as a sort of too new of a cryptography, and it wasn't clear what was their use. And I think by now that we have 7 drafts, the pitch is not even about adding features. It's more like, let's remove code. So yeah.
Okay, thank you very much.
Good morning. I'm James Parker, and I'm a researcher at Galois. Today I'll be talking about some work in progress towards verifying the Jolt ZKVM. This is joint work with a great team at Galois and our collaborators at University of Cambridge and Lindy Labs. So to give some motivation for this work, I think we all know how great zero-knowledge proofs are. In the context of blockchain, they're used to allow smart contract updates and transactions to be validated quickly. So this gives us improvements in terms of gas fees and improves throughput. So one problem is that ZK statements are very complex. Oftentimes they're very large and they're hard to verify. So you want to have some assurance that they're actually correct. So our solution to this problem is to formally verify the front-end statements that these ZKVMs make. So in this effort, we're focused on verifying the Jolt ZKVM. In Jolt, their front-end statements are composed of R1CS, lookup tables, and the composition of lookup tables. At least I personally think this is one of the most promising VMs. It has great performance, and I think this design and architecture is much more amenable to formal verification and also performance. Jolt emulates the RISC-V 32-bit IAM machine, and it's developed by Michael, Sam, Rusu, Srinath, and Justin. So just to give like a high-level goal of what we aim to do in the long term, our main goal is to prove soundness of the front-end system. So this breaks down into two main theorems. The first is that for all witness values, if the witness does not correspond to an actual machine word, then basically the circuit should reject that, since it's not a valid instantiation of the machine. And then if the witnesses do correspond to machine words, then the inputs and the outputs of the witness should correspond to the RISC-V semantics. And again, here you can see this statement sort of represented visually, where you have the inputs and outputs of field elements at the top, they're passed into the circuit, and then at the bottom you can see they're converted into machine words and then run through some reference RISC-V semantics. So this is the general approach that we're taking. We're currently in stage 1, which is in progress. So the first thing we're doing is that we're defining a reference RISC-V semantics. So we're using a tool called Sail for this. The next thing we're doing is that we're implementing a DSL in Lean for representing ZK circuits. We call this library ZK Lean. And then the third thing we're doing is we're implementing a tool to automatically extract the circuits from Jolt, and then we're representing them in ZK Lean, so then we can prove properties about them. In a next stage, we are going to aim to prove that the arithmetizations that we're extracting actually match the RISC-V semantics. And then the long-term goal is to actually integrate these proofs into Jolt's CI system so that as the system evolves, it continues to be verified over time. So here's a little bit of background on Sail. Sail is a system developed by Cambridge, and it's a dependently typed DSL, domain-specific language, for specifying instruction set architectures. So at the top, you can see all the models that have been developed in Sail. So you've got x86, ARM, RISC-V, etc. You can pass these models into Sail, and then Sail has a bunch of functionality. So you can extract simulators in C or in OCaml. You can do some automatic property-based testing of these architectures. And what we're focused on is you can extract to different theorem provers, such as Coq or Isabelle, and then prove properties about it. I guess one thing that you'll notice is there's no lean in this picture, so that's what we're aiming to develop. Just to give you a high-level idea of what Sail looks like, Here's like a little bit of an excerpt of the RISC-V model. So here you can see it defines a nice way to convert between the bit code representation of, let's say, an XOR instruction. You can extract all the registers, and then you can define a semantics of this is what should happen when you execute the XOR instruction, right? So you're just reading from each register, performing the XOR instruction, and then writing back to that register, or to the destination register. So like I mentioned, we're building a backend in Sail for Lean, so this should allow you to extract any Sail model into Lean, and then once it's in Lean, this will give us a golden reference RISC-V semantics that we can prove equivalent to the Jolt machine. But in general, this should be useful for others as well who want to prove properties about Sail models in Lean. And again, this is in collaboration with Cambridge and Lindy Labs. So I'll mention some of the challenges that we've been running into in this conversion. One of them is that Lean doesn't have pattern guards, right? So you can see there's this like if condition on a pattern guard. So basically, this requires us to expand out these conditions, and this causes a bunch of like nested conditionals. So that was one thing we had to support. And then another thing is that Sail has a refinement type system, so it reasons about things like numerics automatically using an SMT solver. But once you convert these into like a dependently typed language like Lean, Lean's had a bit of a struggle to unify these dependent types automatically. So we've had to do some coercions and some wrappers around functions like bit vector append to make sure that the system actually compiles that we are extracting. So here's the current status of our RISC-V model. It's currently about 100,000 lines of code, and we're working on simplifying this and making it better. And we're down to 2 errors. This was much, much higher before, but there's like one more error around dealing with loops and mutating values. So since this is our reference semantics, we want to actually make sure it's correct. So instead of just blindly trusting our backend extraction, we want to test it. So we're using some standardized test suites for RISC-V. We're doing like some differential and property-based testing. And we're also integrating all this into Sail so that this stays correct over time as well. So I'll talk a little bit about ZK Lean. So this is our DSL in Lean for representing ZK statements. So the primary goal of the system is that we want it to be amenable to verification, and then also the automatic extraction of statements from other languages into Lean. So initially, we're supporting the systems that Jolt requires. So again, this is our own CS, lookup tables, and the composition of lookup tables. And the goal is to make the language easily extensible so that you can add other features that other backend systems might require. And I think already today we could probably support most systems like Plonk or Air or whatever your favorite backend is. Here's a little example of what the language looks like. It's a monadic language. So it's like you have this builder monad that allows you to construct your circuits. You can witness new field elements. So now this is like a field element in the circuit. And then you can add constraints. So it's like pretty basic here. Just you're asserting that x is either 0 or 1, right? Yeah, and then I guess one nice thing is it's polymorphic over the field, so it doesn't really matter. You can whatever field you choose, it works for that. So in Jolt has subtables or lookup tables, and it defines subtables by defining the multilinear extension of what the table is. So here you can see we have this function that defines a subtable from the multilinear extension, and all you have to do is give a lambda that defines how to evaluate the MLE. Yeah, I guess one thing additionally to note is that Jolt breaks up lookup tables into smaller lookup tables that are of size inputs 2 to the 8. And then it composes these smaller, like 8-bit lookup tables into larger lookup tables, like 32-bit lookup tables, by using these composition functions. So here's how you represent this in ZK-Lean. So you can see here you're defining these are all the subtables that you use for all the chunks of the 32-bit machine word. And then this function here declares how do you combine these things together to get the higher 32-bit representation. So the final part of our current effort is to automatically extract Jolt circuits into this ZK-Lean language that I just described. Jolt is implemented in Rust, so we want a way to automatically extract this so that as Jolt evolves, we can continue to get an updated representation. So we've implemented a Rust binary function that will link into Jolt's implementation as a library, and then this will automatically extract all the AST representations of the circuit, and then this outputs ZK-Lean as lean files on the file system, which you can then use to reason about. So at the top here, you can see this is like the Jolt Rust implementation of the, I think this is the EEC subtable. Yeah, that's right. Yeah, and this is basically constraining that either X and Y are both 0 or they're both 1. And then here you can see this is our automatic extraction into ZK-Lean. So we already have these representations available so that we can prove properties about them later. This is the extraction of what the R1CS constraints in Jolt look like. This is basically for each step of execution in the RISC-V model. You're given the current CPU state, so these are like a bunch of inputs like witness values, and it's nice that we can represent these in structs, so then if you want to reference like a given witness value, you can just like do a field access. So this is I think will be much more easy to reason about and instead of just like an array of field elements or something like that. Yeah, and here you can see, this is constraining a flag to be 0 or 1. And then here's like a conditional of like combining a bunch of chunks, like all the 8-bit chunks into the 32-bit chunk. I guess one thing to mention is that we did find a small performance optimization already. So as we were doing our extraction, we noticed this subtable is being created. But the subtable was always returning 0, which is not actually useful for any computation. So we were actually able to remove this, and it gave us a small, like 2% improvement in Jolt. So small win already, but hopefully the verification effort will potentially lead to more. Yeah, so like I mentioned, our long-term goal is we want to integrate with Jolt CI. This will allow us to maintain the verification of Jolt over time as it evolves, and we can detect when theorems break. And maybe a future idea or dream is maybe these proofs can automatically be repaired using like AI techniques or tactics or SMT solvers. Yep. So here's a summary, I guess maybe more of like a picture of what we're aiming to do. So we have Jolt's code base in Rust. We extract it into ZK-Lean. Now we have the sail model of RISC-V, and we're extracting it also into Lean, and then we're going to aim to develop this equivalence proof. So, thank you.
Any questions?
What is, maybe you can just succinctly clarify this for me, what's sort of the fundamental difference in purpose and what's included in ZK-Lean and ZK-Lib?
ZK-Lean is a Lean library that allows you to encode like front-end statements, like and that kind of thing. And my understanding of ZKlib, it's more of a back-end focused system where they want to prove that the cryptographic implementations are correct.
Okay, does ZK-Lean depend on ZKlib or not at all?
No, we only depend on MathLib, which gives us like fields and maybe some theorems about them.
Right, thank you.
Mm-hmm.
Sorry, two basic questions. First, if I have other circuits that are not the Jolt VM, would ZK-Lean essentially? So I guess what you're trying to do there in that right green box is just represent the Jolt circuit as you have a polynomial a multivariate polynomial representation of that. Is that what you ultimately?
So right now, ZK-Lean is like representing the circuit. Right now, we only support R1CS and these lookup tables in terms of like MLEs. So I guess, is there like a particular system you're thinking of that you want to?
So if I wanted to build a circuit for SHA-256, and then I wanted to prove that it was equivalent to some spec of SHA-256,
right.
I would want to use that right column of yours, because I would have essentially a formal spec of SHA-256 comes from Wikipedia, and I would have a circuit, and I would like to do the equivalence proof. And I'm just wondering if you've built any of the infrastructure to help in that component. And then you can imagine, ECDSA and other components.
Yeah, so you would have to encode your circuit into ZK-Lean, so like this part here. And then you'd have to have some reference implementation. So like you would probably write the spec, or maybe like this would be where like ZKlib might come into play, where you have like the implementation of SHA in ZKlib or something. And then you can prove that the circuit is enforcing.
How are you doing the equivalence? By some sort of refinement, or like, how are you planning to do it in that?
Yeah, so we define a semantics for ZK-Lean. So like, this is what a circuit means, and then you can prove that the like evaluation of the circuit and all of its constraints are equivalent to whatever the reference is.
Have you compared your RISC-V formalization with the ones that have been used in Anger? I think of the one in ComCert, the one in SL4, the one in KCML. I once counted 4 different formalizations in ROC, and there might even be more. So 200 lines of code sounds like a lot, but maybe that's just because it's generated code.
Yeah, I think, so it's generated code. We're working on simplifying this. I think there's also things you can do to specialize, like, oh, this is a 32-bit machine, and we don't use these extensions, so we can throw them away. But I do think some of the handwritten specs are probably smaller, more simpler, more easier to reason about. But I do think maybe the cell spec is more hardened, since it has been more battle tested.
I mean, SCL4 is used in industry quite widely. So
yeah, sure. Yeah.
Thanks.
Mm-hmm.
What do you think of the trade-offs between, say, having a higher level spec of some primitive like SHA-256 or ECDSA or whatever, and then proving equivalence between that and the Jolt circuit, and between that and RISC-V, versus proving equivalence between the circuit and some sequential reference like RISC-V directly, because it seems to me that maybe your reference is going to use, it may already have optimizations, and it may use particular representations for the abstract variables, and you don't necessarily want to impose those choices on your circuit because they may require different trade-offs.
I'm not sure I followed the question. So I think as long as you have a representation of the, like a reference semantics, you should be able to prove it equivalent. I mean, if they are equivalent, but it might be like more or less amenable to the verification effort.
So on the slide you have the RISC-V model of whatever you're trying to prove equivalent in the circuit, right?
Mm-hmm.
But why that rather than a more abstract mathematical model of the primitive?
So I guess like the Jolt circuit is emulating the RISC-V machine. So So the RISC-V model is the thing we want the circuit to be equivalent to.
Okay.
How do you translate Rust to Lean, and why do you expect it to be correct?
So we build like a direct AST representation. So Jolt already has this for RNCS, so it's basically a pretty printer. And then the lookup tables, we can emulate the execution to build an AST, and then it's also just a printer. And then we also have tests that evaluate the MLE in Rust, and then the AST representation, and we can prove that those, or we execute them, test them to prove that they're equivalent. Yeah. So there is some. So it is part of the trusted computing base that we're pretty printing correct, but it's pretty, I think, reasonable to inspect it manually.
Yeah, you could consider using Aeneas or maybe Hex, or Virus is also thinking about a Lean backend.
Yeah. We looked into these tools, but we thought at least with Jolt we could easily get the AST ourselves, and reasoning about maybe the semantics that these tools require might make the proofs more difficult. But yeah, it's up for
Yeah, you can do everything in one go.
Yeah. Mm.
Anyone else?
So you said that you are planning to fix the theorem when something changed in the Rust side. How that works without breaking the theorem?
Yeah. So when say the Jolt front end changes, the CI will run our extraction again and then rerun the theorems. And if the theorems break, then like the CI will prevent the merging of the code before the theorems are fixed. Ideally, we have some automation that will like automatically fix the theorems as the front end changes, but that is maybe a future work kind of thing. So.
Anyone else? Okay, thank you very much.
Yeah, so hi everyone, I'm Tobias, I'm an undergraduate at TUM, and I'll talk a bit about my work on formal verification of polynomial commitment schemes, specifically the KCG. This work is in Isabel. I kind of prepared this presentation before I knew how big the Ethereum Foundation formalization in Lean was, so I'll talk about this a bit in the end, but just keep that in mind. To kind of see where this work lies in the realm of formal verification, I illustrated a little picture. I call it the Tower of Formal Verification. So here on top you have the paper proofs. So these are the first formal proof by hands, just the proofs you're used to from reading the papers. And then second instance, formal verification of these proofs. So in a theorem prover like Lean or Isabel. So these are the machine-checked proofs. And then again, as the last instance, formal verification of implementations, where I mean with formal verification of implementations, more that the source code is proven equivalent to a certain specification. And yeah, this talk will be solely about the second layer, so formal verification of cryptographic proofs. And yeah, the rest of this talk will basically split up into two parts. The first one will be about the about the formal verification tool I used and formal verification methodology in general. And then the second one will be about the actual contents of this work. The motivation behind this is to kind of show you what is the soundness of these proofs and the quality, but also the limitations, of course. So yeah, let's get right into it. So I used Cryptol. Yeah, Cryptol is a framework specifically designed for cryptographic proofs in Isabel. Isabel is a proof assistant. If you know it, if you don't know it, it's like Coq or Lean. So essentially, how it works is it's based on higher order logic in Isabel's case. So you have a small verifier that essentially checks these higher order logic statements, and then on top of that, you have more complex and better user-friendlier frameworks like Cryptol, for example. In Isabel's case, this verifier kernel is written in standard ML, which is a very strongly typed language, and it's been used for decades at this point, so really this is as good as you can get, I think, for tools like this. So essentially minimal assumptions for maximal security. So then about Cryptol. So how does Cryptol work? On a high level, Cryptol follows the sequence of games approach. I'm sure most of you are somewhat familiar with that. Still, for those who don't, I'll go quickly over it. The basic assumption is you have these games as probability spaces, and then you define this sequence of games, starting with game 1, then game 2, and so on, till game n. Game 1 is typically your attack game, game n, your hardness assumption game. And then what you do, you hop from one game to the next, every time proving that the difference between winning the first game is negligible due to the winning the second game, like I and I plus 1, I guess. And how do these game hops look like? I want to talk about two specific game hops. The first one being the bridging step. So this is essentially just restating your game. Here I swapped A and A prime. I mean, this can be more complex and more complex games, of course. And the second one is the game hop based on a failure event. So essentially you have two games that behave the same, except for a certain event, this failure event, which of course can only or should only occur with a negligible probability. So these two games differ only with negligible. The difference between those games is only negligible. In this example game, we obviously see that on the right-hand side, if we sample A as 0, which I include because we're computer scientists, then you're going to have a hard time on the right-hand side, while the left-hand side has still some probability to win. So in that case, these two differ, but in every other case, these two should be relatively the same. So why am I talking about these two game hops specifically? So these are specifically optimized in Isabel. So like I said, Isabel is general purpose like Lean, so you can do essentially any kind of game hop. But yeah, there's really great tooling for these two. And in my formalization and formal verification of the KZJ, used only these two, and you really can go a long way with these two. Right. So let's take a look at how these games look in Isabel. So here's an example. This is the same game on the left-hand side in Isabel, of course. And as you can say, these look roughly the same. I mean, on the left-hand side, we have this try do else block, but other than that, that should look fairly similar. So formally, these games in Isabels are monads over subprobability mass functions. If you don't really know what that is, don't worry, you can just see it's basically the same. And this try to else block, the purpose of that is basically to accommodate for the sub probability mass function, namely to capture the case of non-termination, or if something goes wrong, like the division by 0 in the last game. And yeah, essentially for this sequence of games proofs, we define these games in Isabelle, and then we justify each game hop with theorems in Isabelle. So I brought a little example. Don't be shocked now, it might look a bit much, but yeah, don't worry. The important part is I have something like this, right? So you see we have these try, do, else blocks here again, right? So these are all single games, so we have 4 games. And then we have these also have blocks, right? And these also have blocks, they're always statements we want to prove. So we also always have point should be equal to this new game. So essentially a bridging step. And these 3 points, they always refer to the game above. So these 3 points refer to that game. And right below, we always have this justification in Isabelle. Here it is by simp add, and then we have some facts. And these facts are basically setting the equivalence for the bridging step. So here's one cute example below. So we have here the one-time pad, and we see here in this game we have C as a uniformly randomly sampled value, and then in the game above we see, okay, there's something complicated going on. Now, this is some Isabelle stuff with the map SPMF and the lambdas and some functional programming, but essentially it's just adding either M0 or M1 to a uniform random value. And obviously we can use a one-time pad to make it a bit easier. Yeah, this is a real-world example. So this is not from my proofs because, polynomial commitment scheme games are a bit larger, so that would not fit quite on the page. But these are from Pearson commitments from the hiding proof. So yeah, but the really nice thing about this kind of proving is that essentially if you trust Isabelle, you can say, okay, so these steps, they're all correct. So the only thing I need to do is to verify the first game and the last game. So this is quite convenient because the first game we always said is the attack game and the last game is the hardness assumption game. So essentially I don't have to worry about these map SPMF stuff and weird Isabelle stuff. I can just look at the playing games that should look almost the same as the games you know and love. So yeah, to sum it up, in Cryptol and Isabelle we have this very small verifier, so we are basically as secure as it gets. We have the sequence of game style proof, so we really only need to audit the first game and the last game, so the hardness assumption game and the attack game, which makes auditability of these proofs basically a thing of minutes. And we have these games as monads, at least for the attack game and the hardness assumption game. These should also be very easily auditable for non-formal verification or Isabelle experts, so just your regular cryptographer. Right, so that's it about the Cryptol part. Now let's get to the contents of this work, like the work I actually did, and that is, firstly, I formalized an abstract polynomial commitment scheme in Isabelle, including all the security games you have, like polynomial binding, evaluation binding, hiding, knowledge soundness, correctness, just your usual stuff. And then I instantiated this abstract polynomial commitment scheme with the standard KZG. I proved basically everything that's possible, so virtually everything except hiding. And then to kind of show the versatility of this definition, I also formalized a batched version of the KZG, so the one where you're batching evaluations. We'll get a bit more to that later. And of course, also proved all possible security properties for that. And to go one step further, I also proved a property called weak hiding for the standard KZG. I'll get to that in the next slide, one of the next slides. Yeah, and to kind of really sum it up, we all know the KZG knowledge sound is usually proven in the AGM. I mocked that in my proofs now, but yeah, I currently am formalizing that properly in Isabelle. Yeah, so let's take a look at how it looks. Concretely in Isabelle, we have this abstract polynomial commitment scheme defined as a locale. A locale in Isabelle is comparable to a trait in Rust, or I think it's interface in Java. So really, we assume we have these few functions, just the standard polynomial commitment scheme functions. And then we can do stuff with them, define games, for example. Like I said, I defined all the standard security games. So here's one example of the evaluation binding game. So there is some more Isabelle stuff, like where this is actually a function, and we take an evaluation binding adversary, and we get a Boolean SPMF. Yeah, this Boolean SPMF is basically capturing if the adversary has won the game or not. And yeah, I think this part here is probably most important for you, and I think it should look fairly familiar. And then additional to defining the games, I also define the advantages for the adversary. So I do not define concrete security statements like, statistical binding, computational hiding, and so on. I leave that to the concrete instantiations, but basically give the instantiators all the tools they need at hand, namely the advantage of the adversary. That's basically their only task to reduce that and say, okay, that is 0 or negligible. Now let's take a look at the actual work I did. So like I said, the standard KZG, these are all the properties I proved. So I will not go into the proofs because I think that's probably a bit too much. But about the weak hiding point, so we all know the standard KZG is not hiding, but in fact it is hiding for uniformly random polynomials. Yeah, how sensible that is, okay. But there's actually this nice thing we can do in Isabelle. So like I said, games are functions, and in Isabelle, if you want to prove a statement about a function and you have uninitialized parameters, these are assumed to be arbitrary, so you have no assumptions whatsoever. So we can very easily make games more strict by just initializing these parameters. So for the hiding game, we can just initialize the polynomial to be uniformly random, and just like that, we don't have the possibility of error in somehow mingling with the hiding game. We can just use the formalized one, and yeah, this property it was a bit hard to formalize, but it's another story. On top of that, the batch KZG, basically prove all the same properties, so completeness, binding, evaluation binding, and knowledge soundness. The weak hiding proof is another thing. I didn't do that. We can talk afterwards if you're interested in that. So it's basically, like I said, it's evaluation batching. So it's not a typical Planck-like batching where you take multiple polynomials and evaluate them in a batch, but it's rather batching the multiple evaluations of one polynomial. So just to be clear about that. All right, so sorry, forgot a little anecdote. So I don't know if you ever checked out like the KZG paper, and be it the ePrint version or AsiaCrypt. Try it and try to look for the proofs. They won't be there. They're only on an extended version that is somewhere on some Waterloo server. So if you have never gone that far, I guess you don't have to anymore, except for educational purposes, of course. Right. Now, to the AGM. So since it's a cryptography event, I'm going to spare you all the functional programming, magic, and monads and functors and so on. Basically, the random oracle model is already formalized in Isabelle, and they did a really nice thing where they have you can see it as a compiler from types. So all the games I defined are in the standard model, but you can very easily in Isabelle port them to the random oracle model with this new type. Then has access to oracle, shared oracle, and you can log the oracle queries and so on. And basically, we're doing something similar for the AGM, so logging group elements. But that is work in progress. I cannot tell you too much about that. I think that's it about the AGM. So we all know polynomial commitment schemes are interesting on their own, but of course they are even more interesting in the context of more primitives and even complexity theory, and that's why I wanted to show you a little, I call it ZK Isabel. I mean, of course, it's kind of an ecosystem for snarks more than in ZK, but yeah, here are a few things that are already formalized in Isabel. So we have the sum check protocol, we have the random oracle model, we have Peterson commitments, and a few other commitment schemes. We have the Sigma protocols, and we have really an extensive array of algebra and number theory. And, well, polynomial commitment schemes are only the latest addition to that. Of course, there's like one big thing missing to kind of bring this thing home, and that would be IOPs and Fiat-Shamir, which kind of brings me to the future work. So obviously, if you have IOPs and Fiat-Shamir, you can formalize all kinds of polynomial commitment schemes, like error-correcting code base like Fry, Were, Binias, Stir, basically all the work that got me excited last year at ZKP6 and this year again. And also interactive based multilinear polynomial commitment schemes like Zeromorph and the one used in Halo. And of course, the biggest name, Snarks. And with this extensive, or I don't want to say extensive, but with this array of primitives already formalized, we can not only formalize, I say, basic Snarks like Plonk, but also, I mean, more advanced ones, folding schemes, for example. But yeah, the main disadvantage we have in Isabel is, I mean, we don't really have that big of a funding as Lean with the Ethereum Foundation has. And also these formalizations, every one of them is kind of singly handled, step by step, so to say. And I mean, I really like the approach of the Ethereum Foundation, doing it all in a modular way, co-designing everything, really doing a library. So I want to actually scrap what I said last, and yeah, just do it in Lean. I guess this yeah, I guess it's kind of obsolete, but yeah. And I think yeah, just to have a little summary. So what did we do concretely in this work? We formalized an abstract polynomial commitment scheme in Isabel. We instantiated 2 concrete KZG versions and transformed the paper proofs into more rigorous sequence of game style proofs. Yeah, we formalized these proofs and currently are formalizing the AGM in Isabel. Yeah, next stops IOPs. I guess that's for Lean then. Yeah, that's it about it. You can find the paper I submitted here and the GitHub code on my website, which I actually just created for this like a week ago. And yeah, I'm happy to discuss afterwards. This was the meme I wanted to share, but I guess it's more like this now. Okay, thank you.
So you said that because your formalization of the AGM wasn't available, you mocked that out in the proof for PCSs. How does that work? Say more about that.
I mean, essentially, you have to twinkle a bit with the types, right? So now the adversary type, you basically add types to also send you the vectors. And then you put some asserts under that and saying, okay, this vector is actually the group value. So yeah, it's pretty ugly. So yeah.
Thank you.
Any questions?
Yeah. So.
Oh yeah.
You said, of course, the thing you have to verify is the first statement and the last statement. Do you have in your slides any example of like the algebraic assumption that, for example, that you use to prove binding or hiding or anything like that? What's your end statement? It has to be some cryptographic.
Yeah. So I mean, yeah, good point. I should have probably put that on the slides. I only have an attack game, but like similar to the attack game, you can also define a game for a discrete log or something like that, and or TSDH in the case of Isabel should look fairly similar. I can show you afterwards if you want to see it.
QSDH has this parameter where you get Q of these things, right? So you were able to model that?
Yeah, sure. I mean, like I said, these games are always like kind of functions. So essentially what you do is you provide another argument to the function, namely how many of these instances you want to have, and that's how it works.
Thanks, this is really nice work. You're building on the PhD thesis of David Butler, doing the commitment schemes and the Sigma protocols. We already ported that to SS-proof. So in ROC, it's also available. So that would be a lot faster to port. And I also recommend everyone to look at that work in other provers, because it really helps to do your formalization, even though the details are different. Thanks.
Thank you.
Anyone else?
So I have one quick question. I haven't done anything in Isabel. I think last time I did things in Isabel was 2016. How did you find working with the AFP, and was there any kind of thing missing there?
I mean, working with the AFP is fairly easy. So I think that wasn't the hard part. But of course, there were some hard parts with, for example, there was no formalization of pairing, so you kind of have to do assumptions about that, and preparing everything about that around that is, was a bit of a pain.
Yeah, we're missing pairings in Lean as well, so I was curious about that specifically.
Okay.
Can you explain the AFP?
AFP is the archive of form proofs in Isabel, which is somewhat dissimilar to like MassComp in RONC or MassLib in Lean, in the sense that it's a bit more like a collection of papers than a kind of nice, software library. And it's a bit chaotic sometimes as a result.
Yeah, but at least from my experience, it's defined very modular. You always have these abstract schemes, and I mean, you can. I even used it in the abstract polynomial commitment schemes for the normal binding, so polynomial binding.
Fantastic. Anything else?
Okay, thank you everyone. And we're gonna have a coffee break, but before we have the coffee break and fill our bellies with a lot of butter, we're gonna take a group photo of everybody, and we're gonna take it in the stairs leading to the lobby. So if you guys can go there before you take a croissant.
the verified verifier, which is an effort, combined effort between ZKProof.org and the ZKVM formal verification effort. This is a few words on what we're trying to achieve, giving motivation, and trying to explain what is the difficulty of proving an end-to-end formal verifier for or formal verification of a zero-knowledge proof verifier. So first, just what are we doing? We're trying to have an end-to-end proof in Lean for Plonk, the Plonk zero-knowledge proof scheme, the verifier of Plonk, so not all of Plonk, and we targeted Ethereum as the specific embodiment, the specific implementation of verifier. Now, why did we choose all these choices? The main push to, first of all, choose the work on verifying a verifier. So you know that zero-knowledge proof, ZKProof.org is trying to standardize for the benefit of the industry. And the place where zero-knowledge proofs are used the most today, and I would say the stakes are the highest, are where they're used to hold billions of dollars worth of cryptocurrency, and this is on ZK EVMs. This is also the motivation for the ZK EVM formal verification project, which has a much bigger task of proving all of the ZK EVM mechanism. But we're tasked with the very last part of it, because the most common, very last step when a ZK EVM did its job is to verify the proof of this ZK EVM using a wrapper, sometimes in Groth 16 and sometimes in Plonk, and verifying that on-chain, on a smart contract on Ethereum. So the choice of Ethereum as an ecosystem is, frankly, that's where the highest stakes are. And the choice of trying to verify the smart contract of Plonk or Groth 16 is because this is the very last step. If we have a security issue there might be malicious state changes, even if all of the machinery before is to spec and does everything correctly, which is already a huge endeavor. There's also a pragmatic piece to it, which is, since this is a choice that has been made in the past few months to focus the effort of the industry on formal verification, and this is done in the Ethereum ecosystem, we are trying to align to that effort and make decisions or embrace the opinions from the bigger effort, the ZKVM effort, which means that we're choosing Lean as the language that will connect or will prove end-to-end the verified verifier. And faced with the choice between Groth 16 and Plonk, so last year I was standing before this crowd, or a combination of this crowd, and talking about let's formalize Groth 16. We're not committed to that. It turns out that we need to formalize Plonk because that has a wider industry appeal. Mainly because of the lack of trusted setup and personal choices of leaders in the Ethereum ecosystem that were actually live tweeting back in Berlin, no Groth 16, do something else. So we heard. Trusted but? Trusted but not not circuit specific, exactly. By the way, those opinions, if these leaders could express them on Blue Sky, even better. I reiterate, everybody move to Blue Sky. All right, so hopefully you have the motivation. Why are we doing a verified verifier with these choices? One last choice is Rust. Even though the main client in Ethereum is written in Go, it looks like if we do the end-to-end verification in Rust, we are a little bit better, let's say, future-proof. But that, I would say, that's maybe the least pragmatic and most compromise of the entire set of choices. Okay, so what are we doing? We're trying to have an end-to-end proof. And we actually are very ambitious with this end-to-end proof, because we start with a paper, the Planck paper. And actually, one of the co-authors of the paper, Oana, is helping us with this effort. And we want to prove that the verification of a Planck, express the verification of a Planck in Lean, and prove its security. So this is a sort of almost like a side quest, because it opens up so much. Everything that's not already available in Lean for us, we will need to work on. So, for example, we heard on the first day that there's some issues with just taking Fiat Shamir and not reasoning on how secure it is in the specific context you're using it. And there's a Fiat Shamir hidden in every little zero-knowledge proof scheme. So just approaching that part, it's part of the paper, but it's a sentence there. To do non-interactive, we do what everyone else is doing. But in order to express that in Lean, we need to have much more detail. Same goes with, the underlying cryptography. If you're using pairing verification to verify your Planck, well, what's pairing? Like, how do you express that in Lean, and what's the mathematics behind pairing? And if there's one thing that I've learned through the years, I don't know the math there, but I've seen people react to the math of pairing. I would describe it as, if I don't have to touch it, I don't want to touch it. But we have to, because otherwise, how do we express, what's actually happening in a verification of a Planck? So there's a challenge just doing that part of proving the Planck paper. Just expressing with a deep enough level of detail, what is verifying Planck. Then here we have, I would say, somewhat of a departure from the ZKVM effort, because this effort is really looking in the future and seeing what are the tools that are going to survive for years and years. But at ZKProof, we're, structurally, we're looking at the past. We're trying to see what are the schemes that have survived the years and are ready for standardization, and what are the schemes that are deployed today out there. So we are not concerned with proving or expressing something in Lean and then executing that or creating code from that. We're concerned with blessing existing code that are deployed and protecting billions of dollars, and going from the existing to Lean. And it's this opposite direction allows us to bless a particular existing Planck out there. So there's a second group of people in this effort that is looking at a Planck smart contract, actually the bytecode of that contract, and extracting what exactly is this contract doing today as it is deployed. And hopefully, we can get with enough steps to express what it's doing in Lean. And then some of the steps that this program is doing is calling precompiles in the EVM client. The main precompile is verification of the pairing. So that's written in Rust for the client that we chose. So we need to extract what exists today in the cryptography of that client and express it in Lean. None of this is easy or trivial, and there's teams of people that are going to be doing this for the next few months. I hope we'll have first results to report in the next few months. But there's an additional step, which is, okay, well, all these extractions from the paper and from the existing Solidity and the existing Rust code, are they all doing the same thing? Like, is this pairing, implementation and the cryptography behind it, is this what the Plonk paper was talking about? And we're hoping to connect all of this with a backbone of Lean. It's a hope. We hope we can achieve it, but it's not clear that it can be done. So there's an element of novelty there. Not doing end-to-end verification by visually comparing extractions and thinking, well, they look kind of the same, so it's probably doing the same thing, but trying to really express the entire existing code in the bytecode of the Solidity program and the precompile, and seeing that it indeed performs a Plonk verification. So if we are successful, the first outcome of this is that the industry can start trusting the chosen Plonk, right? And this is a little bit what ZKProof is trying to achieve. We want to pool the efforts of everyone to a goal that is, let's say, non-controversial in the sense that many industry actors would be using the outcome of this work. And we're trying to do it in a way that creates a sort of playbook so that if others want to formalize other verifiers and other proof systems, well, we set a bar on what it means to be a verified verifier. One big step there is to get the consent of the steering committee and the standardization committee in this organization. These are a group of people that are looking into the details and want to see very serious work and everything explained and tight. And if we reach that, we'll have first, I would say, de facto expression of the standard out there, what is protecting today a lot of money out there in Ethereum, and maybe the story for the next schemes to do the same work. So this is an invitation to be looking at the verified verifier effort. We'll talk about it a little bit later today as part of the breakout to talk about standardization in general and what concrete outcome can we put out there as standards. And maybe in this context, I can also again thank the Ethereum Foundation because of this, I would say, combined effort to push the industry forward with formal verification. We were able to prepare this year's effort, and we're already looking at the next year's conferences and moments where we're going to sync on the progress. So I want to thank again the sponsorship of Ethereum Foundation for this. Thank you. And let's say that those claps are also the claps for the conclusion of this talk, because I want to move to questions if you have any questions. And I think I did not plant a question, but you will always have one, right?
So you said that, so we were trying to verify existing smart contracts. So let's say, for example, that we have a contract that is using the BN254 precompile. The estimated security of that is 102 bits against special tower NFS. That estimate is from Givich and Singh 2021. That might not be secure against powerful government adversaries, potentially. Should we only verify a contract using the BLS 12381 precompile? Because we only consider that adequate for close to 128-bit security.
So that's exactly the trade-off of do we try to be future-proof, or do we try to cover, just quickly secure one demonstration of a verified verifier that's maybe the most common today, even though we know its limitations. I don't have an answer. Oh, that's what I was hoping for.
So with respect to the precompiles, so I think it's like verifying both precompiles is not an issue, and then people will use whatever they use. So I recently did process a grant to use Ferris to verify the BLS precompile in RVM, and then as part of this, because the one that most people use is the BN2541, we'll be looking at that as well, and then people can make up their own minds and deal with risk as they like. Yeah.
So you're seeing here a snapshot of the dynamics of the verified verifier, which is, we know what we're trying to achieve, but there's people with opinion and funding and other groups working on other things that are interacting with our effort. The job of integrating all of these groups is tremendous. I'm very happy that we're kind of a leaf in that tree and not having to do too much, but even what I described in this graph, there's 4 or 5 teams that would be working on this and need to coordinate between themselves. So we're happy to offload that part from the wider coordination. But the short answer is there's many opinions that we can adopt on the fly. One big one is which Plonk? Which Plonk? Which Plonk?
Oh, yeah, I just wanted to ask, kind of like at what level is there, or what level is the plan to verify the pairings? So will you be considering like abstract pairings, or is the idea to consider particular instantiations of pairings on curves?
Particular instantiation, and not just that. I think list authority is going to take some of that work. We're probably going to be contributing to the Lean math library in doing so. So this is going to be reusable for.
Yeah, I was actually just about to say that, because a non-trivial amount of stuff that goes into pairings is also going to be useful for Kevin Buzzard's formal verification of Fermat's last theorem.
That's our hope. That's our hope. It's kind of the overarching theme of ZKEVM FV is that we're multiplying the goals, and one of the goals is to be also useful generally for mathematicians. Alex, you want to add to this?
So with respect to Kevin Buzzard's FLT project, one current issue with a lot of the elliptic curve things in MATLAB is that they're not very computation friendly. And Kevin Buzzard, for his effort, would probably not care that much about this, but for us, we'll have to obviously work a bit around that, and once we have fixed plans in place, we'll determine exactly how to do this.
Thank you for the overview. I just want to advertise one thing that came out of the, I mean, this really resonates with what we've been doing in the HEX workshops for the past couple of years, of course. So I think that's great. So one product that came out of that is the HEX spec language, which precisely does what you're trying to do. So standardization of protocols using Rust. There's currently backends in F-star and Rock, but adding Lean would be really simple, and I think that would fit greatly what you're doing. So I'm wondering whether the standardization that you're using also considers standardizing reference implementations or code.
So I'm not a part of the HEX group, but there's a lot of overlap, and we tried to do to have this conference sort of in tandem with HEX and play with the topic so that we have all of you guys that were in HEX in the past 2 days join us. And zooming out, the tools there are probably very useful for anyone doing this type of work. I expect the different groups working on the different pieces to be knowledgeable and to bring that knowledge into the effort if it's relevant. We're trying to have a scope that is feasible in about 6 months, which is to say the engineers in the group talked about 3 months, so 6 months. Yeah, I don't want to scare anyone. So, and so if those tools accelerate us, fine, but the instruction is basically pick what you are the most comfortable with that does give us a sort of lean backbone at the end, and that is not pre-disqualified because it doesn't fit some other constraint in the wider ZKVM world. So if they're aware of those tools and they're useful, they'll be picked up.
Yeah, thanks.
Any other questions?
Over there.
Thank you. So 3 years ago, if you ask someone to formalize cryptography using Lean, most of the people say it's impossible because you have to do so much previous work that make it unfeasible, and Isabel and other proving systems were kind of the way to go. So I guess Lean 4 changed that, or why we are so much into Lean now? Thank you.
There's a previous iteration of this slide that had the word EasyCrypt all over the place, and we actually have a sort of advisory group from I don't know if I can say this like this, but we have an advisory group from EasyCrypt that have a button that says "I told you so," that they can press 5 times over the project, but not more. Every time we're gonna hit a wall with Lean being a little bit difficult to work with, they may press that button, but only in a constructive way. Like, tell us what exactly we need to learn from what you've already done 10 years ago in EasyCrypt, and we will re-implement it for the benefit of the Lean community if we can. So this has baked into it the work of figuring out that part. Yes, cryptographers have their preferred tools, but also those tools are known by the cryptographers that wrote them, which is 5 people on the planet. And there's only one button, right? So last question, Pablo.
So which Plonk are you aiming for, and does the fact that you're putting a lot of effort into the paper will constrain your choice on the concrete scheme?
Yes, so the answer to that will be realized all together this afternoon. We are leaning to vanilla Plonk, just because it's a good basis. I had a back and forth with Dara Emma about is it vanilla Plonk with the security bug that was there, or is it vanilla Plonk with the iteration that solved the problem? It's with the iteration that solved the problem, right, Joanna? Yes, yeah, sure. So yes, there's a lot to pick from, but in the end, our goal is to both demonstrate a concrete artifact. Here's the actual binary that does verification correctly, but also appeal to as much of the industry as possible, maybe with like, describing as future work how to move to Flonk or to something else. There's a hidden agenda here of, if this is attractive enough, the security of it, maybe some ZK VMs might think that this is a good choice to wrap what they're doing and move to that. Maybe all the Groth 16 ones will want to move to that, or maybe, I don't know, but that's a community decision. All right, thank you very much, everyone. And myself, I don't know. And
Okay, so hello, good morning everyone. I'm Pablo Castellanos, and today I want to present Plink, a new domain-specific language for generating probably correct constraints for the Plonk protocol. And this is joint work with Ignacio, Dario, and Niki. So first of all, let me start by saying why we want to verify these constraints. So as we know, zero-knowledge protocols allow us to prove that we know some secret value, some secret witness, that satisfies some kind of relation. And in the particular case of general purpose zero-knowledge protocols, this can be any MP relation at all. The catch, of course, is that this relation needs to be encoded in a very specific way using some kind of system of equations. And of course, we don't want to be writing something like this by hand because it's very easy to make a mistake and it's not even clear what this means just by looking at it, right? So along the years, people have been coming up with new domain-specific languages to describe these kind of relationships in a higher level way, so it is easier to write. So when using one of these domain-specific languages, the process is something like this. It all starts with some relation that the user has in mind. This is some kind of mathematical relation, and then the user has to put in the effort of encoding this relation in some kind of high-level, hopefully, domain-specific language. So this is just some kind of programming language. And after this, it is the job of the compiler to deal with this program and to generate the constraint system from it. And usually the compiler has some kind of intermediate representation that is hopefully simpler. And in the particular case of zero-knowledge protocols, a very natural representation would be something like an arithmetic circuit, right? And finally, the compiler takes this simplified version and produces the constraint system that we need for the protocol. So this is great in practice. In theory, but in practice, there can be some errors, right? Actually, there has been some research on what kind of vulnerabilities may arise when using this kind of zero-knowledge systems, and some classes of these vulnerabilities have to do precisely with these kinds of languages. The first of these classes of problems have to do with the fact that these DSLs may still be quite low level, so they can be hard to write, and they can lack some common security features like type systems that we are used to in some other programming languages. So this makes it easier to write an incorrect program accidentally. And the second of these classes has to do with the fact that the compilers themselves can contain errors. So this means they can produce some incorrect constraint systems, so either over-constraint or under-constraint, even when starting with a correct description of the program that we care about. So basically in this arithmetization pipeline, we can locate these classes. The first one would be in the first stage of the pipeline, so where there is a mismatch between what the user has in mind and what they actually write in the program. And the second class has to do with the compiler stages of the pipeline. And because of these issues, researchers have been focusing on building formal methods into these languages. And these are some of the examples of these DSLs that include formal methods in some point or another. So Leo, Coda, and Clap are a few examples of this. And well, as you can see from the table, they all focus on verifying different aspects of this arithmetization pipeline. For example, the type system in Coda makes it harder to write an incorrect program at the high level, while the compilers of Leo and Clap are proven to be correct. And also, as you can see, all of them are using a number of different theorem provers to carry out these proofs. To put things into perspective, this is where our work comes in this table. And as you can see, it is both written in and verified using Liquid Haskell. So many of you may be familiar with the programming language Haskell. For example, Cardano is implemented in Haskell. But what exactly is Liquid Haskell? So in short, Liquid Haskell is a refinement type checker for Haskell. What this means is that it is a tool that allows us to refine the types that are already there in a Haskell program to give more information in them. And up here, I think this is probably easiest to see with an example. So up here I have just a natural implementation of the Fibonacci function in Haskell. And here in the second line, we can see the Haskell type. So this is saying that fib is a function from int to int. You give it an integer and you get back another integer. But if you look closely at the implementation, you will notice that if you give it a negative number as an input, it will enter an infinite loop and it will fail to return a value, right? So this is something we can prevent using Liquid Haskell. We can refine the type of the input to be not only any integer whatsoever, but an integer that is greater than or equal to 0. And by doing this, we can be sure that the function is actually going to return a value in the end. And on top of doing that, we can also prove some properties about the value that is going to be returned by the function. In this case, we are proving that the result, f, is going to be at least as large as the input. This is just an example of something we may prove using Liquid Haskell. So this is good because having a stronger type system means we can catch more errors at compile time, but we can also take it one step further, because essentially, if we are clever enough about what we write in these type signatures, we are able to use Liquid Haskell as a theorem prover, right? So this is an example of something we may state using Liquid Haskell. So this is the statement that fib is a monotonic function. So you give me some natural number x and some natural number y that is greater than x, and as a result, I'm going to try to prove to you that fib of x is less than or equal to fib of y. And crucially, this is referring to this exact implementation fib. So this is proving things about the actual Haskell implementation. This is something similar to what you may do in Lean, for example. So with this introduction out of the way, let us start to take a look at Blink and what we can do with it. So Blink is an embedded domain-specific language in Haskell, in particular using Liquid Haskell. It is designed to be declarative, so it is quite high level, and it has support for some basic types. In particular, right now we are supporting booleans, field elements, and vectors of those. And well, it also has a witness generator, which generates both the output of the overall program and all of the intermediate values. And this is just a summary of what the compiler is doing, but I'll get back to this later on. Before, I want to show an example of what we can write using Blink. So I want to take a look in particular at the modular addition, in particular addition modulo some power of 2. Now this is well known by now, and the standard technique to encode this using block constraints is to start by introducing a new Boolean variable that represents whether there is going to be an overflow or not when doing the addition. We are going to add some equality constraint that says that x plus y is going to be exactly equal to c when there is no overflow, and equal to c plus 2 to the e when there is an overflow. And actually, this is not enough. We also need to encode that c is in the correct range. So it is between 0 and 2 to the e. This is a bit trickier, but we can just express this by saying that c can be encoded using e bits. Okay, so how can we write this in Blink? We start by writing a Haskell function. So this is one function that takes the exponent e and the values x and y. And we can just directly write this constraint that I was talking about directly in Blink. So we can assert that b is a Boolean value, we can assert that x plus y is going to be equal to what we want it to be, and we can assert that c can be encoded using a bits. In this case, this is done with auxiliary function to binary, which it is basically introducing a vector of e bits, and it is adding the constraint that c is equal to the binary expansion of this bit vector. And finally, we return c because this is the value of the modular addition. We are talking about these variables, so of course first we should declare them, and this can be done just by giving them a name and a type. In this case, both of these variables b and c are given the type of field. And since we are declaring variables, we are introducing variables out of thin air, we should also give some hints to the witness generator on how to compute the value of these variables. Right? This is done with this other auxiliary function, and it takes as argument this expression in parentheses, which is just a Haskell function, and this is saying how to compute the value from the other values that are already present in the program. So in the case of b, for example, this is a function that, given the values x and y, is going to say, okay, if x plus y is less than the modulus, then there is no overflow, so I return 0, otherwise I return 1. So the good thing about this is that since this is just a Haskell expression, this is very intuitive. You can just know what it means by looking at it. And well, similarly for C. And finally, we can also add some types to this. So the Haskell type of this function takes two DSL programs and returns some other program. But using Liquid Haskell, we can give more information about this. Right? We can refine the type of this DSL program to be not any DSL program at all, but some DSL program of type field. And this is basically a type alias that is declared up here in the right. And given these values x and y, if they are of type field, the result is also going to be of type field, and we can prove this using Liquid Haskell. So now coming back to this slide, I want to just give a brief overview of what the compiler is doing. So what we just saw is an example of this high-level program. So this is what the user would write. And the first thing that the compiler does with this program is to remove all of the syntactic sugar to make our lives easier. But the most important part is that it is assigning output wires to each of the sub-expressions that appear in the program. And this will become important later on. But I do want to stress that this transformation is designed to be very small. So this intermediate representation is by design close to the high-level program. And finally, once the compiler has the intermediate representation, it just adds the equations that are needed by relating the values with the assigned wires. So at the beginning, I talked about verified generation of constraints. So what exactly are we verifying in this program, in this project? Informally, what we are proving is that this last step of compilation exactly preserves the semantics of the program. To be a bit more concrete, what we are proving is this theorem, which is saying that given some program written in this intermediate representation, any evaluation of the variables that appear in the program are going to satisfy the semantics of the program if and only if it is a solution to the constraint system we get as a result of the compilation process. Because this is an if and only if we have both completeness and soundness. So there are a few remarks I want to make about this theorem. So first of all, you will notice that we are talking about the intermediate representation all the time. And this is actually needed because we need some way of referring to the intermediate values of the program, and this is done through the wires of expressions. Secondly, one nice thing is that we are proving this about the actual Haskell implementation of the compiler. This is in contrast with some other approach, which would be to implement the compiler and then separately to model this implementation in a proof assistant and proof correctness of this model. Now, this would introduce some potential source of errors, so we are avoiding that, and this is one of the reasons why we chose Liquid Haskell. And finally, I want to stress that this proof is completely modular. So in the case where we want to add some extra instructions to the language, we can just extend it, and the proof is not going to be affected by the new thing. And well, this was our primary goal for this project, to verify the correctness of the compiler, that it preserves the semantics. But since we are already using Liquid Haskell, there are some additional properties that we can prove about our program. So as an example, I want to take a look at this padding function from SAR to 56. So this is basically a function that ensures that the input message is going to have a length that is a multiple of 512. Right? So it has a whole number of blocks. What this function does is it takes the message and appends a 1, then appends a bunch of zeros, and finally it appends the length of the message using 64 bits. Of course, if we want to do this, we should make sure that the message is not too long. So it can be encoded actually using 64 bits. And this is something we can express using Liquid Haskell like this. So by doing this, we can be sure that we will never be able to call this function with a message that is too long. And once we have this, we can actually prove the property that we care about. So its length is going to be actually a multiple of 512. So at this point, I have to admit that I skipped a little bit of information in this compiler pipeline, because any compiler needs to do some kind of optimizations to get better code, right? For whatever definition of better that we care about. In the particular case of zero-knowledge languages, what we care about is the number of constraints, because this essentially translates into the proving time. So we implemented some optimizations in our language. And up here we have an example of a program P that the user could write. And if we look at it, we'll see that it's just a description of this arithmetic circuit, which would get translated into this big system of equations. But if we take a closer look, we'll see that it has something like 3 minus 1. This is just a constant, this is 2, so we can substitute it in. And if we do that, we'll see that we end up with 2 times x plus y, which is just a linear combination, and this can be actually encoded more efficiently. So our compiler is smart enough to notice these kind of things, and it can replace what the user wrote by this simpler expression that gets compiled into only one constraint. So this is of course good, we want this, but we are changing what the user wrote, so of course we should make sure that we are not changing what the user actually meant. This is precisely what we are proving in this theorem, which informally says that if a program has some value under some optimizations, under some evaluation, after doing optimization is still going to have the same value. And well, again, both the implementation of the optimizations and the proof of correctness are completely modular. So if we want to add some more optimizations, we can do that without interfering with the rest. Okay. So after all of this work, of course, we wanted to test our language on a real example. So we chose to implement SHA-256 using Blink to see how well it works. To do this, we started by implementing some standard library functions, like the modular addition I talked about, some bitwise logical operators, or some operations on vectors, like shifts and rotations, this kind of thing. The first thing we notice is that many of these operations can be implemented just in the same way as you would implement them in Haskell. So we believe this is very intuitive for the programmer. And well, all of these functions together took a bit over 200 lines of Haskell code, plus Liquid Haskell annotations. And once we have all of these components, we can basically combine them into just a standard functional implementation of SHA, which is also quite close. It follows the same pattern, basically, as it would do in Haskell. So if you know how to implement SHA in Haskell, you can model this pretty closely in Blink and have an implementation in Blink. And again, this used a little bit over 200 lines of Liquid Haskell code. And one of the things we wanted to test in this benchmark was how our optimizations were doing. So we ran this hash function using a number of inputs with different numbers of blocks, and we counted the number of constraints as well getting generated. What we noticed is that we are generating around 80k constraints per each block, which we believe is a decent number, especially considering we are not using either lookup tables or custom gates. So I want to finish by saying some things that we are not currently implementing in the language, but we believe it could be interesting to look into in the future. The first of these is verification of what the user writes of the program. So I talked about these constraints for implementing the modular addition, but it is not so clear that these are actually encoding the modular addition of x plus y. And for example, if we drop this last constraint, it is no longer the case. We can find some values for b and c that are still going to satisfy these constraints, but are not going to encode what we want with the modular addition. So, but the thing is, this is not so easy to notice, so we would like to verify this. And we believe Liquid Haskell can be a good tool for doing this, because the user can just write the specification, as I showed, and try to prove that these constraints are the same as the specification that the user wrote. So just to be clear, this would mean to try to bridge the gap here. So try to make it harder for the user to write something that they didn't actually intend. And the second thing, as I mentioned, we are not supporting either lookup tables or custom gates. So of course, we would like to implement this in the future, and hopefully also verifying that they are correct. Well, So to sum up, I presented Blink, a new domain-specific language for Plonk. It is a declarative language with support for some basic types, and both the compiler itself and the optimizations that we do on the language are verified. Finally, we tested our language by implementing the SHA-256 hash function. So that's the end of the presentation. Thank you very much.
Any questions?
There's an error on one of the slides, but I wanted to try and turn it into a constructive question about liquid Haskell. Fibonacci of 2 equals 1, which is not raised to equal 10. If you actually tried to write that in liquid Haskell, would it automatically have found that error in the counterexample? Because if you try to do the proof for n greater than or equal to 2, and you get fib n greater than or equal to 2n minus 3, so you fail to do the inductive step.
I'm sorry, can you rephrase the question?
So to what extent does liquid Haskell give you sort of understandable errors when you make a mistake in function refinement declaration?
So I'm not sure I understand the question, but liquid Haskell just does understand when you make when you code some program that doesn't satisfy the specification, and it signals that as a type error. So you are not able to compile the Haskell code if you have a type error. This is just like that.
Okay. I was just wondering how much information does it give you about what you've done wrong in that case?
So because this is just done at the type analysis level, it gives you exactly the thing that, or the type that it knows the code has, and what you claim it does. And it says, okay, these do not match.
Okay.
Yeah, so I tried liquid Haskell before, and so there are certain things that it seems you can't do, like when you have to write the function in a certain way, or liquid Haskell would not work sometimes, like some syntactic sugar or stuff like that. So I'm wondering if during your work you had any issues with that, or it was just me. Thank you.
Okay, so yes, liquid Haskell works on any Haskell program. You do not need any special syntax. So the way it is designed is the specification works as a comment. So if you disable liquid Haskell, you just have a Haskell program and you can add specifications or whatever.
No, sorry. What I mean is that you have to write sometimes the function in a certain way for the refinement to work.
To be able to prove the refinement,
yeah,
yes.
So I had a hard time trying to prove certain stuff, and after modifying the function in a certain way, you make the refinements work. But if you write in normal Haskell, sometimes the refinement will not work.
Yes, so this is a common theme with verifying code. There are times where you need to write code in a specific way so that the machine can, for example, prove that some invariant works. This is usually the case if you are familiar with Lean, for example. There are times where you need to write some function to prove some invariant, or Daphne, or any of these languages that have verification in them.
Yeah. I have a question as well. Well, thanks for the presentation. It was very nice. My question is about the optimizations that you mentioned. If I understood the theorem correctly, you essentially show that after the optimizations, your witness would still be a valid witness. Is that the case?
Okay, so
yeah, if you can go back.
Okay, what is this? So this is this doesn't mention witnesses. This is doing at the high level program, basically.
Yeah. So what I mean is that you show it's equivalent on one direction. So you make some optimizations. Does it work on the other way around as well? Like how do you prove equivalence?
Okay, I see.
It both ways?
It does work in the other direction in most of the cases. So you are able to prove that they have both the unoptimized version and optimized version have exactly the same semantics. But there are some cases in which this fails. For example, if you have a multiplication by 0, then you may have some undefined value multiplied by 0, and you want to optimize that to become 0. So you have something that is not defined on one end, and something that has a value and is 0 on the other end. So because of this reason, we needed to state the theorem in this way, but we can actually prove the stronger theorem that you mentioned in a lot of the cases. Yes.
Okay, thank you.
There's work on embedding Haskell into the ROC proof assistant, and so there was a comparison between liquid Haskell and using ROC as to do the proofs, and actually doing the proofs in ROC it turns out to give better usability. The main person behind that, Joachim Breitner, he's now working at the Lean Foundation, and I hear some gossip that they're thinking about making a Lean backend for something like liquid Haskell, so that might be a road for the future.
Yes, I know there are people working on translating liquid Haskell to ROC, as a matter of fact, so yes, I think it's a very interesting topic.
Yeah, thanks.
Anyone else?
Did you explore using any of the CVC5 finite field solvers?
Sorry, can you repeat?
Did you look at integrating the new CVC5 finite field solvers into like liquid fixed point?
Okay, yes, there is work on that. I think it is quite close to getting finished, actually.
Cool, thanks.
Okay, thank you.
Okay, good day everyone. I'm Masato Tsumi from Waseda University. Today I'm going to be presenting my research on benchmarking ZKVMs, efficiency, bottlenecks, and best practices. Let me begin by explaining the fundamental concept of ZKVMs. A ZKVM is a technology that proves the correct execution of arbitrary computer programs. The operation of ZKVMs consists of two steps. For example, if you have a program that calculates nth Fibonacci number, we first executed it with input n, and then produces the execution trace. This execution trace includes like memory blue and opcode for each instruction step of the program. Next, we generate a proof based on this trace. The verifier can then verify the proof, for instance, that the 10th Fibonacci is equal to 55 without having to re-execute it themselves. During the proof generation, the ZKVM proves the state transition of the VM at each execution step using snarks. When a program is compiled, it expands into instructions such as add, load, store, and so on. When the ith instruction is executed, the VM's memory, register, and program counter value transition to the next state. And to prove the state transition, three basic proofs are required. First, instruction encoding proof, proving the encoding from binary to instruction is correct. Second, read-write memory consistency proof, proving the value purportedly returned by any read operation is equal to the value most recently written to the appropriate memory cell. And third, instruction proof, proving that the instruction execution results are correct. By repeating these proofs for each execution step, we guarantee the validity of the final execution result. A major application of ZKVMs is scaling Ethereum smart contract. Ethereum validators can update the Ethereum state by verifying the proof instead of re-executing the blocks on their EVMs. And this allows transaction fees to remain constant, regardless of any program complexity. And one thing to note here is that ZKVM is not necessarily designed for privacy protection. Their primary purpose is to make computation results efficiently verifiable through snacks. Currently, many ZKVMs claims to be the fastest, but they actually measured under different conditions, making it difficult to compare objectively. And systems started as the fastest often has limitations such as enormous memory consumptions or only works for specific programs. Therefore, we built a standardized benchmark framework to comprehensively compare and analyze multiple implementations across various evaluations and target programs. There is significant value in presenting standard benchmarks from a neutral community like ZKProof. A familiar example is large language models. They usually cite benchmark scores as the evidence of performance when releasing new models. Furthermore, our research identified the CPU and memory bottlenecks for each project. And we also estimated the best practices for leveraging existing ZKVMs. We compared mainly 7 projects, SP1, RISC-0, and Jolt for both CPU and GPU implementation, and OpenVM, ZKM, Nexus, Novanet for only CPU, as they don't yet have GPU implementation, and Seno for only parallel performance for 100K Fibonacci, as they don't yet have SDKs. So let me introduce some ZKVM implementation briefly. RISC-0, SP1, OpenVM, ZKM adopt similar approaches. Proof generation involves 4 steps: execution trace segmentation, and proving, proof aggregation, and stack to snark. And the approach from execution trace segmentation to proof aggregation, like a parallel ways, called continuation. And common feature is the adoption of fry stack-based proof systems. Use 32-bit fields to efficiently generate proofs. Seno also uses the continuation, and the major difference is its adoption of GKR proof system. And Jolt currently doesn't support continuation. And Jolt adopts the lasso lookup arguments, which looks up the results from the pre-executed result table instead of executing instructions through circuits. And Nexus currently uses Store, fry stack-based systems produced by Stackware, but originally adopts Nova-based folding schemes. And Novanet uses both the folding scheme and Nebular, which provides efficient memory checking argument and switchboard technology. As shown in this table, the fry stack system is the most popular right now, and all projects except Jolt supports continuation. And another important technique is precompiles, which allows certain operations like hash functions or signatures to be proven by custom circuits much more efficiently than compiling them to ISS. And there are variations in precompile support, and this support can significantly impact the prover time efficiency. And the rest of my presentation proceeds as follows. For our comparison, we run benchmarks on the AWS EC2 instances equipped by 64V CPUs, 256 GB RAM, and 24 GB GPU memory. And we compared the 7 projects mentioned earlier. And test programs included calculating the 100K Fibonacci number and SHA-2 2048, and ECDSA verification on K256, and EVM execution on a simple 100 ETH transfer transactions. And evaluations are primarily divided into time efficiency and memory efficiency. For time efficiency, we first compared prover time. Next, we evaluated program generalizability based on whether proof generation could be completed within 1 minute. Then we compared increases in prover time when changing input size. And finally, we compared efficiency improvements when changing the number of CPU cores. And for memory efficiency, we compared peak memory usage. And the benchmark programs are publicly available on GitHub, allowing anyone to reproduce our results. And when a program is executed, each ZKVM calculates cycle count to estimate the proving cost. And cycle count is calculated based on the trace, following some rules, such as 1 cycle counts for addition instructions and 4 cycle counts for memory access instructions. But these rules are a little bit different among projects. And surprisingly, we observed variations among projects in cycle counts, even for the same projects. For example, for the 100K Fibonacci program, SP1 cycle counts was only 600K. And for RISC-0, the cycle counts was about 2.4 million. Such large differences suggest that the number of cycles are reduced through the use of precompiles or some optimization techniques. So moving on to comparisons, this graph shows proof generation time for 100K Fibonacci program by CPUs. And OpenVM was the fastest, was only 11 seconds in prover time. And with SP1 and Jolt showing the next best efficiency. And that graph includes the 3 other programs alongside Fibonacci. From top to bottom, Fibonacci, SHA-2, and ECDS and ETH transfer. And first, even with the similar cycle counts, prover times differ. SP1 and RISC-0 both have 5 million cycles for ETH transfer program. But prover time was vastly different in 46 seconds and 321 seconds, respectively. And OpenVM was the most efficient across all 4 programs. And for SHA-2 programs, Jolt was also very fast at just 5 seconds. And next, this graph shows the results for GPU performance for SP1 and RISC-0 and Jolt. And SP1 and RISC-0 were much more efficient than their CPU implementations. And Jolt shows little difference as they only support GPU acceleration for some components. And notably, SP1 generated proof for EVM execution for only 4.7 seconds. And while some more complex contract execution need to be compared, achieving to 12-second real-time proving is promising for practical applications. So overall, SP1's GPU was the fastest and followed by RISC-Zero's GPU and OpenVM's CPU. And at the time of the paper submission, we had compared only 5 projects and 2 programs, Fibonacci and matrix operations. And following ZKProof 7 reviews, we expanded to 7 projects and also added programs like SHA-2 ECDSA verification and EVM executions, and which are much closer to real-world use cases. And the NovaNet team made significant contributions, such as including supporting EVM executions, and we greatly appreciate their helps. And this table visualizes whether proof generation could be completed within 1 minute. And SP1, RISC-Zero, and OpenVM cleared this threshold for all programs, demonstrating sufficient program generalizability. And ZKM cleared 1, and Jolt cleared 2 of these thresholds. And this graph shows how proof generation time increases as Fibonacci's input size changes from 10, 100,000, 10,000, 100,000. And Nexus and NovaNet became unmeasurable after a certain point due to accessible time requirements. And most implementations shows super linear increases in proof time with input size n. This means the linear time increases with the input with the cycle counts. And RISC-Zero and Jolt and ZKM showed high increase rate, while SP1 had the lowest rate, showcasing its efficiency for large-scale programs. To measure the parallel performance, we measured the proof generation time with varying the number of CPU cores from 2, 4, 8, and 12. And the left shows the result for 1,000 Fibonacci program, and the right shows the for 100K Fibonacci program. And here we compare only for SP1 and Nexus and Seno. The comparisons for other projects remain for future work. And we observed efficiency improvement of up to 8x. And larger programs appear to benefit more from increased core counts. However, there are limits to efficiency gains from parallelization. In both programs, using more than 8 cores resulted in either small improvements or even decreased efficiency. And this occurs when parallel processing overhead exceeds gains. Therefore, it's important to select an appropriate core count based on program scale. Regarding the comparison on peak memory usage for 100K Fibonacci by CPU, notable is ZKM's large 83 gigabyte peak memory usage. Meanwhile, Nexus and NovaNet maintain constant memory usage even with increasing input size. However, as we saw earlier, they trade this for significantly lower time efficiency. And this is for GPU's peak memory usage performance. And SP1 and RISC-Zero achieved much lower memory usage during GPUs, However, they used around 24 GPU memory instead. And Jolt showed real difference memory efficiency between CPU and GPU. So overall, RISC-Zero's GPU and SP1's GPU were the most memory efficient, and while Nexus and NovaNet were most efficient by CPUs. However, when measuring it on ECDC verification locally, we observed even higher peak memory usage. While NovaNet and Nexus consistently maintain low values, ZKM and Jolt reached about 110 gigabytes, and others reached about 30 to 50 gigabytes. We summarized in this table the most time-consuming processes as CPU bottlenecks and the processes running during memory peaks as memory bottlenecks. For example, Jolt's CPU bottlenecks were Lasso Samsec protocol and Spartan, and polynomial generation in Lasso lookup table was the memory bottlenecks. And this bottleneck analysis was based on the visualizing frame graph. And please contact us if you'd like to know more about this analysis. Here are the guidelines for best ZKVM selection and specification based on resources and requirements. For ZKVM selection criteria, SP1, RISC-Zero, and OpenVM seem to be good for general purpose use cases. And it's recommended to use ZKVMs that supports the precompiles need for your specific programs. And it's recommended to measure the most efficient core currents for proof generation. And for GPU specifications, 24 GPU memory is required for running SP1 Jolt, SP1 RISC-Zero. And for memory specifications, at least 32 gigabyte RAM is recommended for general purposes. And using Jolt and ZKM may require 120 gigabyte RAM or more in some cases. That concludes our research. Future challenges for our benchmark framework include more detailed bottleneck analysis and support additional new ZKVM projects like Bolida and Pico, as well as the latest version of current projects, and support for programs with wider applications such as float and matrix operations, and complete comparisons for processing efficiency. We will continue working on these challenges for further enhancing the stability of our ZKVM benchmark framework. And of course, we are so welcome for your contributions. Please flag up pull requests or issues to our repository. That's it. Thank you for your attention.
So I have one quick question. So one important thing that you highlighted is obviously the memory consistency checks. Have you noticed, or are you able to evaluate, let's say you take two different sorting algorithms, you run them on the ZKVM, and one of them has a random memory access pattern and one of them has sequential memory access patterns. Like, could you tell ahead of time like how much overhead that would add, particularly for ZKVMs that have continuations and where you'd have to enforce consistency checks at the boundaries of each chunk that you would then prove in parallel?
Yeah, actually I don't have the answer for that, but yeah, I wanted to more detailed analysis on the bottlenecks, but I want to do it in the future.
Perfect, thank you.
Do you have plans to extend the set of benchmarks to some of the things that have been considered in previous ZKProof conferences, that represent sort of more realistic cryptographic protocols. I've noticed that the benchmarks are basically only checking a deterministic function for particular inputs, which in principle it's either true or false, you can optimize it down to nothing. Whereas if you have a cryptographic protocol that you're trying to implement based on public inputs, then that can't be optimized down to nothing. So the things that we were talking about were like Merkle tree inclusion proofs and so on. Do you have any plans for that?
Sorry, what is?
So there's in previous ZKProof workshops, we've discussed various protocols and benchmarks that would be useful in practice, so beyond just repeating Jadu or repeating Fibonacci or whatever. Do you have plans to go back and look at those suggested benchmarks and implement them?
Yeah, I think the most use cases for ZKVM is proving the Ethereum blocks. So I think, yeah, the performance for proving proof time for proving Ethereum blocks is one matrix, as the ETH proofs are working on that. Yeah, and also, yeah, many ZKVM projects are working on implementing ZKMLs, like proving machine learning by ZKs. So I think such operations like matrix multiplications or activation functions or any other, machine learning operations should be compared.
Yeah, I mean, speaking as a cryptographer and protocol designer, benchmarks like that aren't useful to me because I don't care about machine learning and I don't really care about EVMs, but I'm trying to get an idea of sort of how particular building blocks that are very commonly used in protocols behave on the various platforms.
So I think maybe a question would be, how easy would it be for someone to take your benchmark setup and to try and add a program to that?
Yeah. So I asking setting the benchmark.
So if someone wanted to use your benchmark setup, but to benchmark something that you haven't benchmarked yet, how easy would it be for them to do this and just submit a pull request that says, I've added a couple benchmarks?
Yes, actually setting the benchmark is so difficult because it's running on Linux systems and should install so many tool chains for running so many projects. Yeah, should be make it so easy. But I have prepared our bash script for installing those tool chain as one command for now, but actually should be maintained. Yeah.
Okay. Maybe future work then.
Yeah.
Thank you.
Thank you.
Any other questions?
Thanks for the work. Do you plan also to compare and bench ZK EVMs, which I understand is a little bit difficult to run them out of the box, let me say, but indeed it could be useful?
Yeah, not currently supporting ZK EVM projects. I think it is totally different to compare. Of course, ZK EVM are much more efficient than ZK VM projects. Yeah. But I think I will consider to support these ZK EVM projects.
Thanks.
Okay, thank you. Great talk.
Thank you.
Okay. So, hello everyone. We keep on talking about ZKVM. So this talk is going to be not on formal verification. It's going to be a talk about strong notion of knowledge soundness for ZKVM. So a bit more on the theory side, respect what we've seen in the previous talk. This is a joint work with Matteo and with my student Luigi. So I'm going to be a bit redundant here. We've seen these things already again and again during these days, but let me repeat for all of the people that were sleeping until now. So proof of program execution, there is a verifier and there is a prover. The prover wants to prove that a program P on a public input X and a private input W run and you output Y. And he wants to prove it to the verifier. And there are many ways to do that. Among the most efficient way to do that is to just send a zk-snark that the proof indeed that the program indeed correctly computed Y on input X and W. ZK-snarks are zero knowledge, are non-interactive, are succinct, are argument of knowledge, and that's kind of the solution for this problem, one of the solutions for this problem. So again, I'm going to be redundant again. The classical approach would have been to take your program that you want to prove the execution of. You can compile this program in an intermediate representation or a snark-friendly representation. Let's say R1CS, Plonkish, CCS. And then you would run your ZK-snark on this representation of this program and program P on input X. Let's forget for now about the private input W, output Y, so you use your snark to prove that. The ZKVM approach is instead of compiling a program by program, just compile a CPU. Theoretically, let's call it like a universal circuit, and this universal circuit takes in input both the program and input for the program, and so we get again from the CPU, we go through the intermediate representation, the snark-friendly representation of the CPU, and then we have this universal program, and a ZKVM is just a snark that can prove that the universal circuit on input, the program P, that now you've written on your nice and easy to work with language on input X, output Y. Why we want to do that, I shouldn't insist on why this is a nice way to approach this problem. Some of the reason is for formal verification, so the idea is that you should focus on the formal verification of the circuit and that's it, and then you're good. Apparently that's not true in practice, but in theory should it. And we can use existing languages and tooling and so on. So this is a good approach. So many applications of ZKVM, generic use cases are like proof of solvency, image provenance, content moderation, fancy t-shirt, and so on. The killer application are for blockchain-related applications. I can mention private transaction, private smart contract, ZK rollup. And when we focus on blockchain-related application, we see that we want to send our proof on the blockchain. So now the theoretical question will be, can an adversary, by looking at all proof in the blockchain, somehow break the knowledge soundness of the ZKVM? So this is the question that we're trying to answer in this work. So let me repeat it again. So what we want to fight against are the so-called malleability attack. In this malleability attack, there is an adversary that gets in input proof, so it takes it from the blockchain, and the property that we want to analyze is the fact that an adversary with extra information, for example, a proof, shouldn't be able to modify this proof, change this proof in a way that it can prove a statement for which he doesn't know the witness. So we should be able to extract this proof by star. Of course, the only trivial attack will be the copy-paste attack. This is unevitable. It turns out that these kind of attacks are not ruled out by zero knowledge, neither by knowledge soundness. We need a stronger notion of knowledge soundness. And let me talk a little bit about the stronger notion of knowledge soundness that is needed. So the stronger notion of knowledge soundness that imply non-malleability for zero knowledge snarks is the so-called simulation extractability notion. So what is this simulation extractability notion? It's basically the same image that you see before. Now we have an adversary that has oracle access to the simulator, and the adversary is playing the knowledge soundness game, but in the presence of a simulated proof. And again, here he has to forge a proof for a new statement, meaning that to avoid the trivial copy-paste attack. So the adversary interacts with the zero knowledge simulator and then forge a proof. We need to consider ZKVM that are indeed zero knowledge, and as Alexander mentioned in his talk, ZK in ZKVM is kind of a lie, but in this talk, ZK in ZKVM is true. So let's look at the complexity of ZKVM. We've seen it in the previous talk that ZKVM are very hard and very complex tool, because the idea is that we need to handle a universal circuit, and this universal circuit, we want to fill it up with a lot of instructions. Let's say, for example, the instruction set of RISC-V have more than 50 operations. So we will need a circuit that has a giant switch with all the possible cases. And as we've seen in the previous talk, it's not only that. We need to handle not only the instruction being executed, we also need to handle the fact that, a witness for the ZKVM is just a sequence of snapshots of this virtual machine, and we need to be sure that between step 1 and step 2, there is consistency in this snapshot. So we need to check that the memory is consistent through the entire computation, that the fetch, decode operation are consistent during the execution. So we need to handle RAM, program counter, registers, and so on. Okay, so we wanted to analyze the simulation extractability of ZKVM. First thing that we notice is that almost all the ZKVM follow a modular design. This is just natural, just the correct way to do that is the natural way to do that. We settle down for Jolt, which is a ZKVM based on the lookup singularity. And actually what we propose as a ZKVM that is non-malleable is something that we call a Joltish, which is inspired by Jolt. It's not quite Jolt for some technical reason, including zero knowledge. And these ZKVM are, broadly speaking, divided in two big components. So they are modular and they are divided in a big ZK snark that check memory and check fetch and decode and so on. And then there is a big snark that is for the CPU instruction. So the fact that the XOR was well executed, the AND was well executed, and so on. So this is kind of the ZKVM that I'm considering right now. So the goal of this work was to understand what are the conditions to assess the non-malleability of what we call Joltish. And let's look into this question. So now, in theory, this question can be generalized just a little bit. So instead of the previous question, let's consider the question, what are the conditions for non-malleability of modular composition of snarks? This is a very natural question. And it turns out that trivial composition doesn't work. That seems like easy to show. The fact that if you have snark number 1 that is non-malleable, snark number 2 is non-malleable, you just concatenate these two proofs together. What you obtain is not something that is non-malleable. And the idea is that there are this so-called copy-paste attack. Basically, what I can do is that just to simulate one of the proof and then prove a correct proof for the second one. And this is going to be like I'm proving something that I don't completely know. Okay. Here the problem is that there is no glue between snark 1 and snark 2. So we need to kind of glue them together somehow. And the way to glue things together is by using a commit and proof relationship. So a commit and proof relationship contains in this instance a value X, but also a commitment C. And the kind of statement that it proves is that a predicate P on X and W is equal to 1, and that the witness W is indeed committed in C. Now we can define the conjunction between the commit and proof relationship, which is like the end between two predicates, such that the witness is committed on a commitment C, and this commitment is this witness is shared between the two instances. So we can glue the two relationships together. Okay, what about the non-malleability now of the compiler in which to prove? We give two different compositions, and we show these compositions are indeed non-malleable. Okay, so let's see the first composition. The first composition is the natural one. We have so our prover for the conjunction would, on input x1, x2, and w, what it will do is to commit to w. Then it would use the first snark to prove the relation number 1, the second snark to prove the relation number 2. Now, if the two building blocks are trapdoorless, zero knowledge, and simulation extractable, meaning non-malleable, then the output is going to be simulation extractable and trapdoor zero knowledge. Here I'm not talking you about trapdoorless zero knowledge, it's just a restricted form of zero knowledge, just for technical reason. Okay, it's a notion quite used in the case of random oracle-based zero knowledge schemes. Okay, this seems like natural and easy to prove. Next construction is just incrementally a bit more difficult, not much than that. So what if instead of using a simulation extractable scheme for the snark number 2, we use a signature of knowledge? The construction works as follows. We commit to the witness. We prove using the snark number 1, the first part of the relationship. We prove using snark number 2, the second part of the relationship. And since the second snark is also a signature of knowledge, what we can do is we can sign arbitrary message. And what we're going to sign, the proof of the snark number 1 using the snark number 2. So pi2 is a proof, which is also a signature of knowledge for pi1. So we attach together these two proofs. And now here, it turns out that we can relax the property, the security property required by the snark number 1. And it turns out that this thing is quite useful for us. So the theorem say that if the snark number 1 is witness indistinguishable, knowledge soundness, and efficient witness computable, and the snark number 2 is trapdoor at zero knowledge and a signature of knowledge, then the construction, the compiled snark is simulation extractable. Here, maybe the only notion that you might not be aware of is this efficient witness computability, and this efficient witness compatibility is basically what allows us to do the trick. So the idea of efficient witness computability is that if I can sample the commitment myself, then it's easy to find a witness W for the value x1. Basically, the relationship is almost in P, beside the commitment part. Okay, and here a very, very easy sketch of why this is secure. So the idea is that the zero knowledge simulator for the conjunction can just compute an honest proof pi1, and it needs to simulate the proof for pi2. It can compute an honest proof pi1 because of the efficient witness computability property. And the reduction to the knowledge soundness on snark 1, it's easy because now you don't have to handle the simulator. So we just reduce the knowledge soundness. And now it turns out that this scheme could be completely malleable. So what can we do? To make sure that any malleability attack is kind of avoided, we sign the proof pi1 with the simulation, the signature of knowledge pi2. In this way, every time that an attacker tries to modify pi1, he has to modify also pi2, but pi2 is simulation extractable, so we'll have to forge a valid witness. We could be able to extract a valid witness. So That's the idea of our compiler. Good. So now let's go back to the ZKVM. Let me recall again what is the architecture of a ZKVM, specifically of our Joltish ZKVM. So these two pieces, snark for memory checking, fetch and decode, snark for CPU instruction. The witness is a trace, which is a snapshot, many snapshots, one after the other of the virtual machine. And the idea here is to use the second compiler, the one in which one of the schemes just have to be knowledge sound. And so we assume the snark for memory checking, fetch, and decode, which is basically also the most complicated part of this construction. We just assume it to be knowledge sound. And we need to assume a simulation extractable ZK snark for CPU instruction. And this is going to work. And I'm going to tell you why this is going to work. And basically, the idea is that the snark number one, it is efficiently witness computable. So the idea is that, for example, let's define this simulator for for Joltish. Let's suppose that we feed the simulator with a program P, an input X and Y, and what the prover should do, that P of X is equal to Y over a RISC-V architecture. What the simulator, we can feed the simulator with this P, X, and Y. Let's assume that this is a wrong statement, so that the P of X is equal to a value Y prime, which is different than Y. And the simulator should prove that the P of X is equal to Y on a RISC-V architecture, anyway. So the trick here is that we can hack the instruction set in such a way that by hacking this instruction set, we end up with a program that if we run the program on this hacked instruction set, we actually obtain that P of X is equal to Y. Now we run this program, we obtain a trace of execution of this program, and it turns out that this execution trace is a good trace for the first snark, because we actually executed the program as it is, but on a hacked instruction set. This witness is not going to be a valid witness for the snark number two, but here it's fine because we can use our simulator, and our simulator is a simulation extractable scheme, so it's fine to prove a fake statement for this part of the scheme. Okay. So let's continue non-malleability of Joltish. So this is basically one part of the result that we present in this paper. And so now we want to talk about the lookup singularity. So the idea of ZKVM based on the lookup singularity is the fact that we substitute the snark for execution of instruction using a lookup argument. So what we need really to fill the hole in this construction is to have a simulation extractable lookup argument. Okay. So what is a lookup argument? A lookup argument is a snark that allows to prove that a committed vector f is a subvector of a big table T. Here f is much smaller than T. Here what we want for a lookup argument is that the prover complexity is only proportional to f, or I mean, yeah, it might be proportional to T, but in a way that is like succinct. Lookup arguments right now can handle very big table, as big as the truth table of RISC-V instruction set. So this is the idea behind Jolt in some sense. And what is the lookup argument behind Jolt? It's lasso. So the second part of this paper is really about proving the simulation extractability of lasso. And to prove simulation extractability of lasso, we actually need to first define a zero-knowledge version of lasso. And then we prove a simulation extractability for zero-knowledge lasso using a framework based by this work by Faust et al., which is basically proving trapter zero-knowledge, unique response, special soundness, and this is imply simulation extractability. we extend and improve over a work by DAO and Grab. This is because Lasso is based on Spartan, and Spartan was already proved simulation extractable in that work. And actually, even if I'm just giving one slide to this part of our work, this is indeed where all the mathematical heavy lifting went on. Okay, this is conclude my talk in 20 minutes. So what about future works? So non-malleability, I think an interesting future work would be about the non-malleability of SNARK. Here, looking back, backward, to prove non-malleability of Joltish, we had to first define a zero-knowledge version of Lasso. So this is because the definition, that's definition what they say, you need to have a simulator to formally prove simulation extractability. So what about non-malleability without resorting to simulation extractability? Are there some notion that can capture that? Another thing, and the part of the talk that I emphasized the most wasn't about composition. And here I looked at composition, we looked at composition of commit and proof SNARK, but another tool that is very amenable to composition, which is basically invented for composition, is reduction of knowledge. So what about the non-malleability of reduction of knowledge? Can we have tricks like what I explained before, that only one of the two components needs to be simulation extractable, and then you have it. So you put all the complexity on what where you don't know how to prove simulation extractability, but the last component is going to be simulation extractable, and that's going to fix your task. And as well, a natural question is about non-malleability of other lookup arguments. And that concludes my talk.
Sorry to hog the mic a little bit. Can you comment on the sort of the compositionality of strong simulation extractability versus weak simulation extractability? Because I could be wrong, but I think weak simulation extractability composes more naturally because so to summarize, it allows the proofs to be malleated, but they are committing to the instance, the public variables. And a proof for a given instance doesn't help you to generate proofs for a different instance. So my experience with using that notion, for example, in security arguments for Zcash, is that it's just as easy to assume weak SE because you have to handle pasting of proofs anyway. So would it be easier in general for us to just concentrate on weak SE as the basis of composition?
I think it's really application dependent. I mean, I wouldn't say that weak, I wouldn't call it weak simulation stability and strong.
Yeah, weak is slightly misleading because it is actually quite a strong property.
Yeah. Because, I mean, weak simulation stability, for example, we saw UC security of growth. Growth is randomizable. Randomizability sometimes is kind of a good property that you would like to have. In some other setting, no. When you're using your proof as a token, then in that case, you really want to have strong non-malleability. So maybe the naming weak and strong should be rephrased. I will call it controlled.
Can you give a little more detail about hack the instruction set? What exactly is being done there?
Yeah, I cheat a lot there. So the idea is that so you have your program, and your program has a bunch of instructions, and you can focus on the last extractions that your program has to execute. And now here I'm gonna do just an extraction that instead of the program would say you need to do an add. Now I modify the instruction in the simulator in a way that this instruction instead does a print y. So at the end of this program, this act program will at the end print y, just because I act what was the last instruction that executed. So I'm just renaming this add to do what I want to do. And now I'm proving a false statement for the lookup. The lookup is looking up for 2 plus 2. You should find 5. Instead, they found a y. Right? And that's just a trick. And I'm proving something false, but I'm proving something false using a simulation extractable lookup argument. So in terms of security, I'm fine. Does it make sense? Thanks.
I didn't understand.
Well,
any other questions? Okay, thank you.
Yes, so I'll talk to you about how to use Hex for correct and secure zero-knowledge implementations. So first, the question we want to help answer is, can we actually trust online voting? And how do we actually ensure that the security of online voting is implemented by some smart contract? And in this regard, there is also some push to do more high assurance. So there is some EU Data Act about smart contracts. One of the subsections of this act is about robustness and access control, which states that you have to ensure that the smart contracts have been designed to offer a high degree of robustness to avoid functional errors and to withstand manipulation by third parties. And our goal is to show that you can actually do formal verification to get this high assurance, and thereby make formal verification one of the standards for getting high assurance and implementing protocols where it's very critical that they're doing the right thing and are robust, for example, for smart contracts. Another example of this is also the Swiss e-voting regulation, which states that you have to have some form of formal security proof in the computational model for things you do for voting. So another question could be, why is voting even relevant, and also specifically, why is it relevant for blockchains? So voting is used many places inside of blockchains. It's used for consensus, governance, and decentralized organization. Furthermore, the adversarial model inside of blockchains is also very complex. So looking at cases of using these security proofs in the context of smart contracts is also very interesting, because we are working with a very strong adversary, and we can therefore show that we can also have strong adversarial modeling and still get usable results. Furthermore, just in general for voting, the stakes are very high, both societal but also in a financial sense. When working with blockchains, there's a lot of transactions going on, so investing a bit in getting the correctness of your implementations is very relevant and can save a lot of money in that way. And issues in this can be that there can be bugs in both in the specification. So you could have written something where you were imprecise in how exactly you should implement something, and some interpretation of the specification might be wrong. you could have been incorrect in your cryptographic proof on paper, you could have written something wrong, or you had some detail you forgot, or it could be in the implementation, you implement something that doesn't follow the actual specification. Yes, so our process to try to alleviate these problems is to use HACS for writing the specification. So HACS is a framework where for implementing these things, it's done in a safe subset of Rust. The idea is here you can implement the specifications as a runnable specification, and then it has translations to a lot of different backends. So we have some proof frameworks backends. So we have RUC as one, F* is also another, and ProErf is a third. And this framework is very general and encourages a lot of like cross theorem prover, cross tooling interaction. So you could add, for example, Lean as another backend without having to do too much to get there. We then take these things, and for our case, we translate it into RUC. Inside of RUC, we have a security library called ZKProof, where we prove some security properties about this smart contract, this voting protocol. And then we also use Concert to prove functional correctness of the smart contract and prove some trace properties. And then finally, you can take all these proofs on the code, and you can re-extract the code, and you can take some of the re-extracted code and replace some of the elements with more efficient implementation, where we have the libcrux library, which has secure, verified, fast implementations. Yes. So more about HACS. So as I said, HACS is a subset of safe Rust with translations to proof assistance. One of the projects within HACS is HACSpec, which has a goal of making a lot of these internet standards like IETF and NIST more machine readable, so we can actually run them and we can have reference implementations to test against. Even though they might not be efficient implementation, they'll still allow you to do a lot of proofs of correctness on the specification itself, and allow you to have a concrete definition of what the specification is, and alleviate some of the bugs that can be in the specification itself. Yes, and as I say, HACS is a subset of Rust, so you can also actually just run the specification. Here we can take elements of the specification and replace them with efficient parts that we know are secure. So if you have a specification that uses some curve, we can have an efficient implementation of that curve instead of the more high-level specification. Yes. Now for our next tool is ZKProof. So ZKProof is a tool we use to do modular proofs of cryptography. It's a library within RUC. It's a formal way of doing state-separating proofs. And the language inside of ZKProof is a magnetic state and probability-based language. Furthermore, we have a program logic within ZKProof to do reasoning about equalities of programs and manipulation of programs. And that is derived from the categorical Dijkstra-Monad framework. The way you do proofs within ZKProof is this game-hopping style of proofs in the computational model. And ZKProof also has a large library of useful examples. So since it's so modular, you can take protocols or primitives and prove them secure and reuse those proofs and guarantees in larger protocols. Some examples are, we have a lot of the joy of crypto formalized in ZKProof. Next, we have Concert. So Concert is a framework, again, in RUC for doing smart contract certification. The concrete way that Concert works is that it models an abstract account-based blockchain with pure smart contracts. So here we're not working with a lot of state-based things, but a lot of existing blockchain frameworks are also working with functional code. So having this model is not that much of a restriction for actually doing the reasoning we are working on. And we also have some verified compilation to a lot of targets. So when you want to re-extract the smart contract you have verified here, you can extract it to, for example, WASM, but also Rust, Haskell, OCaml, C, and other targets are possible. Now, coming back to our case, is a case of online voting. So more specifically, we're looking at the Open Vote Network Protocol, OVN. The parts in OVN for where we're doing security proofs of a commitment scheme and 2 zero-knowledge proofs. The OVN protocol is quite simple. However, many of the parts are parts you would also use in like larger protocols. So OVN is made for doing boardroom voting, which means that it's voting with like 50 to 100 people or something, but not like large-scale elections. However, you could imagine reusing a lot of these components to prove something like election guard, which is a larger effort for doing actual large-scale votes. Yes. As many of you would know, zero-knowledge proofs are a big part of this. So the zero-knowledge proofs we're using in this this work are the Schnorr protocol and an OR proof for showing whether the vote is a 0 or 1, but not revealing which case. And we're also working a lot with Sigma protocols. So both of these zero-knowledge proofs fall in the category of Sigma protocols. In ZKProof, we have a framework for reasoning about these Sigma protocols. So we can show the security properties of these Sigma protocols by showing the correctness of the protocol by doing computation in ZKProof. We can show special honest verifier zero knowledge by defining a simulator that can construct the transcript given just the response and the challenge. And finally, we have shown simulation sound extractability, where you construct an extractor that, given 2 valid runs for the same witness, gives back the actual input. And having these 3 properties ensures the security of the Sigma protocols we're using, and we have shown these for both the Schnorr protocol and the OR protocol we use in the in So I think this is a stronger guarantee where simulation, but yeah, maybe. Yeah. And as for the protocol in general, so the way the protocol is structured is in 4 different rounds. So in the first round, everyone commits to a public key and publishes the public key on the blockchain. In the second round, everyone checks the commitment and compute a commitment to their vote. In the third round, everyone shows that their vote is either a 0 or 1 and cast their vote. And in the final and fourth round, everyone just validates all the commitments and tally the result. So the protocol is built up in a way where the final result is just a combination of all the parts given, and you end up with it just being the result is in the exponent, so you just brute force the exponent, which is also right. This protocol is not fit for large-scale things, because you would have to brute force an exponent for a very large number if you have like larger elections. The reason here we have round 2 and round 3 being separate instead of just casting the vote and committing to it. The reason we actually have introduced this commitment is that otherwise you would be able to look at how others cast their vote and have that influence how you cast your vote yourself. So therefore we have an extra round with this commitment. There exists a version of this protocol where that is not a thing. Yes, and the properties we want for the full protocol are these 3 top properties. So you want self-tallying, which means that anyone can like audit the result and just tally the votes themselves. This is part of us just publishing the result. It might be hard to do this because you have to brute force this exponent, so it might not be something you want to spend the money to compute. but it is possible to do, and therefore it's also important to have this auditing step for voting protocols. The next property we have is maximum ballot secrecy, which means that you can actually not see what people are voting given the result. So all the ballots are indistinguishable from just some random input, which is the security property we want. And finally, you have universal verifiability, which again has some ordering property, so anyone can verify that the protocol was actually done correctly, so the run of the protocol was done correctly. And this boils down to the zero-knowledge proofs, so having that everyone can validate that both the commitments and the zero-knowledge proofs done throughout the protocol are correct, ensures that we can't change the input, we can't vote 2 instead of 0 or 1 or something like that. Yes. And as I say, the security properties are given for the commitment scheme, and these zero-knowledge proofs are given in ZKProof, and the functional correctness we have shown in concert. Yeah, so we can look at how this actually looks in ZKProof. So here I've written up the protocol and the game jumps we're gonna do. So this is the proof of the maximum ballot secrecy, so showing that we cannot distinguish the input vote from just random noise. So the idea is we basically try to push the secret key sampling all the way through the protocol by step idealizing different parts. So the first step up here is idealizing the discrete lock assumption we have. Next up, the second part is idealizing the Schnorr protocol. The third jump is then we want to idealize again another use of the discrete lock. Fourth step is idealizing the OR protocol, the CDS protocol. And lastly, we can just push it all the way through the tally, which means that we now idealize the entire protocol and shown that we are not actually depending on the input anymore. So no matter what input the user gives, we can show that it's equivalent to a program where the input is just random, so we can distinguish the output of the two programs. Yes. And now for some related work. So instead of doing this verification in ZKProof, you could also look at tools like EasyCrypt. The difference between ZKProof and EasyCrypt is that EasyCrypt is not a foundational framework, whereas ZKProof is a foundational framework, and ZKProof is in the context of the ROC ecosystem, so we have some tools there to help with some things. Then we also have some other projects, some of which are unmaintained. So there's ZKProof and the foundational cryptographic framework FCF and Cryptol, which we heard about a bit earlier. There are also some other styles of provers. So there's some symbolic provers instead of computational. One of these is also present as a backend for Hex. So ProVerif is an existing backend for the Hex framework. Squirrel and Tamarin are other symbolic provers, which could possibly also be added to the Hex framework. And as I mentioned earlier, an alternative voting protocol, which might be more realistic, is the election guard protocol. But for that, there's a bit more off-chain parts, but a lot of the other building blocks are the same. So you'd have to do a bit more reasoning, but the general structure would be the same as what we've done for the OVN protocol. So in conclusion, we have a formalization and an implementation of a zero-knowledge proof, or protocols using zero-knowledge proofs as part of this OVN protocol. This is the first time showing both the correctness and security of some smart contract, and it illustrates possibilities for using formal methods as a requirement for online voting, and trying to push this high assurance also could mean doing actual proofs by creating the tools that makes it easier for everyone to work with proofs and defining proofs. And all of this can actually be made efficient and can run efficiently using the libcrox library for verified cryptographic primitives. Thank you.
Any questions?
I just have an answer to your question from earlier. Simulation sound extractability is just exactly the same thing we call simulation extractability. It was defined by Jens Grott it's an AsiaCrypt 2006 paper. Simulation sound is ZKProofs for practical language and constant size group signatures. Just to clear that up.
Anyone else?
Okay, maybe lunch then. Thanks for the great talk.